Good morning and welcome to everyone joining us both online and in person for the GSSA African Exploration Showcase. So my name is Dr. Zandri Harris-Spear and I am a consulting geologist for a company called BNS Geological. And our focus is essentially as a consulting company with our main focus on 3D geological modeling. And we are also official channel partners for Sequent. So today I'll be presenting to you the processes that we followed for implementing a 3D geological model for the Ngami Copper Project, also known as NCP, within Botswana. And this presentation is given in collaboration with RES, Cobre, and with Sequent. So during this presentation, I'll be covering a brief introduction on the company, from which we will then focus more specifically on the Ngami Copper Project, geographical location, the regional and local geological setting, the structural controls on the mineralization for this deposit, the drilling information and associated data that was used for the construction of this project, the geological and mineralization modeling that was followed, the construction of the mineralization domains, the exploration target estimates that was calculated, as well as our conclusions and recommendations for this project. So just a brief introduction on the company. So BNS Geological is a proudly South African-based company that is 100% Black owned with a level 1 BE accreditation. And we have over 20 years of experience in 3D geological modeling, mineral resource modeling, using both Leapfrog Geo and Datamine software. The focus of our company specifically is on skills development and implementation of best practice geological modeling workflows within the workplace. And we have worked through various regions globally, so Africa, Europe, Australia, South America, and Asia, with our clients ranging from modern to Anglo-American, Rio Tinto, Barrick, and many more. And our client base spans more than 20 countries. And we apply our key technology strengths for both greenfields operations to fully operational mining stages. And we have a broad range of knowledge on different types of deposits, including kimberlite, orogenic shear-hosted, load gold, faulted and folded units, as well as tabular mineral deposits. We are a multifaceted company, so we have different components in which we focus on. So we have our consulting services, in which we focus on 3D geological modeling specifically. So this is for structural types of deposits, doing structural modeling, strata alteration types of modeling, as well as mineralization modeling. We also focus on mineral resource modeling, as well as Leapfrog Geo audits and reviews. We also have an implementation process in which we focus on implementing Leapfrog Geo for companies, as well as then training them up using customized training courses, as well as ongoing geological modeling support and guidance throughout this process. We also have a very comprehensive training program that we offer. So this is both online, in-person, or private sessions, in which we then also offer both basic, intermediate, and advanced courses, as well as our deposit-specific courses that we focus on. So these are our kimberlite courses, our load gold courses, MAPSI models courses, geostats, and coal courses. So these are all related in training Leapfrog Geo on these specific deposit types. And as I mentioned briefly earlier, we are an official channel partner of Sequent, so we also offer the sale of Sequent products. And this includes Leapfrog Geo, Edge, Central, MX Deposit, Imago, and Oasis Montage, just to name a few. So essentially, we are your one-stop shop for anything geological modeling related. So to get into more detail about the actual exploration project, so the Ngami Copper Project, also known as NCP, is located in the western area of Botswana, and is roughly situated 150 kilometers to the southwest of the town of Maun. And the NCP explorations area lies on the northern margins of the Kalahari Copper Belt, also known as the KCB. So the Kalahari Copper Belt has been recognized by the US Geological Survey as one of the most promising regions for undiscovered sedimentary-hosted copper deposits globally. And this NCP exploration site is situated along strike and adjacent to already producing mining operations of Kuprick Canyon's high-grade Zone 5 operations, as well as Sandfire's T3 Mateo copper silver production. The Kalahari Copper Belt, in terms of its regional setting, is located in the Neoproterozoic Damara Thrust Fault Belt and is situated to the northwestern margins of the Kalahari Craton. The Kalahari Copper Belt also stretches discontinuously all the way from the Namibian region all the way to Botswana, and is known for its widespread northeast trending strata-bound and structurally controlled copper and silver mineralization, which is associated to accumulate within rift-related meso to Neoproterozoic volcano-sedimentary basins. In Botswana, this fold belt is referred to as the Ganzi-Chobe zone, and in Namibia is referred to as the Southern Foreland zone. So studies have suggested that the lithostructural controls, along with the permeability of both the metal source as well as the sulfur source and the redundants, were key elements in the precipitation of both copper and silver ores located within this region. The copper and silver mineralization is associated with the regional fault limbs and hinges, which suggest that the structural setting within this area plays a key component in exploration of potential ore trap sites. The Kalahari Copper Belt is characterized by upwards to slightly inclined overturned fault systems with steeply dipping axial planes. The hinges are known to be subhorizontal and plunge both northeast and southwest within this region. And our rocks in this area are considered to be regionally metamorphosed to lower grade green schist facies and locally approaches the amphibolite facies as well. So the NCP exploration site occurs within the northern margins of the Kalahari Copper Belt, and the main focus for the drilling program essentially is designed to intersect both the sedimentary structurally hosted as well as the structurally controlled copper-silver mineralization that is associated with the main redox contact between the oxidized Nguakopan formation, known as NPF, which is our red beds, and the overlying reduced marine sediments of the Dakar formation on the limbs of the anticline structures. So, sorry, it's on this contact for the Dakar and the NPF, and that's where the focus for the exploration occurs. So detailed geological modeling was focused on the northeast southward trending southern antiform, which extends for a period of 40 kilometers across the NCP exploration site, with evidence of anomalous copper and silver mineralization with high density of drilling and sampling occurring within this comet area. There's a lateral continuity of the mineralization that occurs over tens of kilometers of this deposit, both along strike, on both the northern and the southern limb of this mineralization. And an increase in grade has been notable on the eastern side, where the high density of grade distribution resides on this anticline as well. So this is essentially a plan view of the geological model that we have constructed. So you'll see we have regionally a fault system occurs, and the focus for this exploration project resides within the southern limb of, or the southern anticline of the system, where we have both a northern limb as well as a southern limb with multiple targets that have been essentially identified. So the main economical units so far that have been identified with lateral continuity have been within Comet and with its interstellar unit in the south. So in terms of the structural controls on the mineralization, the drilling results indicate that there's a consistent wide intersection of both anomalous to moderate grade copper silver values with extensive strike lengths for structurally controlled high grade zones. And this style of mineralization is dominated by fine grained chalcocite, which occurs along the cleavage planes of S1 and in fractures, rather than the expected vein-hosted bornite and chalcopyrite that has been associated and typical of the rest of the Kalahari Copper Belt units, specifically in Zone 5 at Kamakau. So in terms of the modeling that was done in terms of regional scale, so we've modeled our upper unconformable Kalahari units, which is both consolidated and unconsolidated Kalahari sands. And then we have the Dakar unit, which is marine sediments consisting of sandstone, siltstone, shells, conglomerate, which is the primary host for the mineralization, with the Nguakopan being the underlying unit, where you have red beds of sandstone, siltstone, shells, and mudstones that essentially acts as trap sites for the mineralization. So the contact itself within the deep cave, so the Dakar and the Nguakopan, is essentially where the copper and silver mineralization is hosted. With regards to the structural controls for the mineralization, so early synkinematic quartz veining are generally parallel to S1 and are often associated with fractures due to large competency differences within the host lithology. We also have later synkinematic quartz carbonate veins that are subparallel to S1 and cut open and reopen earlier deformed quartz veins to show internal foliations along your S1 direction. The structurally controlled higher grade zones appear to be related to these quartz veins and quartz carbonate veins, and they have been interpreted as possible conduits for introducing and concentrating the copper-silver mineralization within the NCP area, as well as being remobilized from lower strain domains for hosting structures, and mineralization could be within the bedding planes of S0. So the fracture permeability compartment are sandwiched between two massive sandstone units with minimal porosity and permeability, essentially acting as seals or trap sites for the mineralization. And this compartment or zone of increased permeability appears to run both up and down as well as parallel to subparallel to the NPF DKF contact where we find the majority of the mineralization occurring. So with regards to the drilling information and the database that we have, so the database comprises of a total of 78 drill holes, from which 49 of these drill holes intersect mineralization in the southern antiform, and 49 of these drill holes total approximate 2,665 meters of mineralized sample lengths. The drilling campaigns were conducted in 2014, 2019, 2022, and 2023. And are primarily drilled towards the southeast at 60-degree dip in the northwestern limb and 60-degree dip towards the northwest on the southern limb. So essentially intersecting with the primary focus of this NPF DKF contact. We were able to model on a regional scale the fold with the plunge that it had, and you can see the steeply dipping folds with some localized folding occurring in some target areas. So on the right-hand side, you'll see we have the drill hole intersections with our contact of the DKF NPF being modeled. And these blue discs are essentially the downhole structural data that is guiding and controlling the dip of the surface based on the dip and the azimuth of these structural measurements. So this was the main focus for where we've seen to control our vein modeling, which we will discuss in a moment. So in terms of the mineralization modeling, it is more structurally controlled and associated with the NPF DKF contact specifically. We found that the DKF is mineralized while the NPF contact shows very little mineralization, as it is essentially a sealed trap site for those ores. We have multiple mineralized peaks that are of both the copper and silver that have been observed within the contact, and we found that higher grades tend to be located and predominantly associated to close proximity to this contact. So this contact between our NPF DKF units are essentially where we've picked up our higher grades. So you'll see that this is a trace of a drill hole, and within Leapfrog, you can plot this as a histogram down the drill hole, your assay information. And these are the high-grade peaks of the copper and silver mineralization that we've picked up for this unit, with the contact of the DKF NPF occurring where we've seen the trend where or higher grades of copper and silver are concentrated directly onto that contact. So the mineralized domains are essentially based on the assay information, and we were using Leapfrog Geo's veining tool to easily construct these different veins that we've picked up for the trends based on the contact. The samples for the assays were selected using Leapfrog Geo's interval selection tool to identify discrete mineralized domains. And two cutoffs were chosen for the classification of these domains. We have a high-grade domain with our copper percent more than 0.5%, so Hg, and a low-grade mineralized halo between 0.2 and 0.5% copper, essentially modeling our mineralized halo that consists of low-grade copper with these high-grade vein-like units in between. So essentially, you'll see that we were able then to model these different veins. So we were able to pick up 4 different mineralized units based on the selection of the data. And here you're seeing the combination of all 4 of those different veins. And then cross-section through Comet, you can see that we have 4 distinct veins we were able to pick up as a continuous lateral trend between these drill holes to identify the copper veins. So 4 discrete mineralized halos. So these are low-grade domains were identified on the northern limb and 3 within the southern limb. The high-grade domains were created within each of these low-grade domains itself at a 0.5% cutoff for each domain. So a custom reference surface based on the structural data was used to control the orientation and trend of these veins within your low-grade domains, using Leapfrog's veining tool for the RBF and turbulence, which was then used to calculate both the dip and the azimuth. So DKF NPF surface specifically was used for both the mineralized halo, while the high-grade domain was used its own reference surface based on the orientation of the selection. So you'll see that you have these high-grade zones within the low-grade domain. So in more detail, you'll see you have the mineralized, the mineralized low-grade domains with the high-grade domains modeled within them for the estimation. So this is the distribution of the copper percentage within a section of Comet, just a 3D view, and you can see the distribution of the grade within Comet based on the numerical interpolation function in Leapfrog. We were able then to create this for this whole limb system. So independent consultant CCIC MinRes was used to engage to calculate the mineral targets for this area. And both statistical and geostatistical analysis were performed using Datamine RM, Datamine Studio RM for each of the mineralized domains, which were calculated individually. A 1 meter composite length were deemed to be suitable for the grade estimate within each of the mineralized domains, specifically where the residual was distributed equally for the calculation. A total of 1,452 SG measurements were collected. However, only 127 of these samples fall within the mineralized domain, and therefore an average density of 2.77 was assigned as it was assumed that the SG sample was not adequate for the estimation for the respective domains. So for both the estimations for the copper and the silver, ordinary kriging was used, and the estimations were undertaken using, again, both Datamine Studio RM for the calculation. So based on the exploration target and estimates that we have, 2 categories for the maiden estimate were calculated: exploration target category 1, as well as exploration target category 2. Exploration target category 1 is focused on drill hole spacing between 125 meters and 400 meters apart along the comet and interstellar area, with a further approximate 9,000 meters of drilling required to upgrade this to an inferred resource. And exploration target 2 was focused on limited data with exceeding drill spacing greater than 400 meters, but less than 1,600 meters along strike. So in terms of the tonnages and grade for this, exploration target category 1 has a mean ton of 23.4 million tons with a potential grade of 0.5, and exploration target 2 has 111 million tons at 0.4 mean grade. So based on this locality map that you can see for the southern anticline, you'll see these dots indicate essentially the copper equivalents for these units and the estimates that we have. So you'll see Comet has a higher percentage of copper equivalents on the southern limb on the northern compared to the southern limb. And you'll see in orange here is our category 1, where we have both interstellar and comets as our exploration target 1, and exploration target 2 are these green units with the dashed lines indicated the untested contact of about 20 kilometers. So with regards to our conclusions and recommendations for this section, essentially, our NCP mineralization model uses the veining tool in Leapfrog to construct all the mineralization domains for the NPF and DKF as a reference surface. The resource modeling was done using the ordinary kriging method for both the copper and silver mineralization. And further resource drilling is required to upgrade the exploration target 1 category into an inferred resource, with a further additional 9,000 meters of diamond drilling required to achieve this. And there's also that 20 meters of additional, or 20 kilometers of additional contact that are still untested for this specific project. Thank you. Any questions from your side?
Thanks, Sandri. I saw you reported ranges for the exploration target tonnages. So did you have multiple wireframe models, or how, can you elaborate on how you got those ranges?
Yes. So the ranges was basically done, calculated based on doing a rotated block model in Datamine. So we had multiple wireframes, and for the classification of this, we are allowed to report ranges. Was not done using JORC. It was done on the Australian reporting standards. And for that specific reporting standard, you're allowed to report on the minimum and maximum ranges for the wireframes. Yes, Stefan.
What made you choose ordinary kriging as opposed to any other method? And the second question is, what potential do you think there is towards Chobe and into Zimbabwe, bearing in mind you have the Gwai River mine in northwestern Zimbabwe in the Proterozoic there?
So ordinary kriging in this case just fits the variability of the data a lot better in terms of choosing the estimation method specifically. And I'm sorry, I didn't quite catch your second question.
Northeast in towards Chobe and in across the border into Zimbabwe, bearing in mind that in northwestern Zimbabwe, we know we have the Gwai River copper mine, which is in the Proterozoic there. I think it's a slightly higher grade, but I just wondered, has anybody done any work on estimating the kind of potential there might be in that northeastern extension?
I'm not too sure about the northern section specifically, but from what we've seen based on the lateral continuity of the adjacent mines and then also the potential for this exploration side, we would assume that the potential for exploration as well as the grade would continue, especially because both Sandfire and Kubrick, that's towards the northern section, seems to be quite high grade, even though the mineralization style is slightly different, but we do find that it's quite high grade. So I would definitely say that the potential is quite high to extend and do exploration towards the northern section.
This is going to be slightly different to the other talks that you've already had and the rest of the talks today. The whole concept behind this is that we as geologists tend to fixate on exploring stuff and finding a nice new deposit, but we don't always think in terms of where is our product going to, what is that product used for, and what are the supply and demand constraints on it. So it's all very well and good to go out and look for a battery metal deposit. But the thing is it going to be economically viable either in the short term or the long term? So as with anything, there is a whole load of new abbreviations coming into the market, as Fisa just pointed out. When you start to get involved in this type of stuff, you're going to start reading weird and wonderful acronyms, which automatically you're going to think is just wait, I don't understand how certified reference materials are part of this, but they're not. So the new terminology that's coming into play is that we subdivide, or the world, especially the Western world, is subdividing metals and minerals into what's referred to as critical raw materials. So as you can see there, it's metals and minerals which are geographically discrete. So for example, platinum is dominated by South Africa, Zimbabwe, and to a lesser degree Russia, and those are effectively the sole suppliers of platinum group metals to the rest of the world. So it becomes critical for somewhere like the EU or the US or Japan or Korea if you are making automobiles, for example, because they need platinum for catalysts. In a similar manner, we also refer to, as you will see references to what's SRMs, which are strategic. So these tend more to have military value. It's a terminology that you'll read a lot about in America, but it's also coming into play into Europe because of Europe's relationship or dependency on NATO. And it tends to be slightly more high tech. So as you can see, moving towards space technologies, military technologies, and it tends to be a lot of metals and minerals which are bio co-products from other mineral and deposit sources. And this is a distribution of countries which dominate the market. As you can see, with no surprises, China dominates almost everything. But I want to draw your attention to one or two rather interesting peculiarities which you find when you start investigating this a little bit further. For example, hafnium, dominated by France. Now, France is not a hafnium primary producer. France gets most of its hafnium as a byproduct. It comes from Orano's rutile processing plant, and France effectively dominates the Western supply chain. Hafnium coming from America is a byproduct of their heavy mineral sands mining. So their zircon has a very high hafnium content. And hafnium, for those of you who are not aware, is used in the nuclear industry. So again, it has a strategic advantage for countries. Niobium of interest, between 72 and 92% of the world's niobium is supplied by a single deposit in Brazil which is a deeply weathered carbonatite horizon. Because it's free dig, again, it is one of the lowest cost producers in the world, and almost every single Western economy that uses niobium is dependent on sources coming out of Brazil. Lithium coming out of Australia, effectively again dominated by a single deposit, Greenbushes. There are a number of other hard rock lithium deposits in that belt, but again, Greenbushes effectively dominates all lithium production coming out of Australia. South African is pretty obvious, I think, to everybody as well as the DRC. So it's just trying to understand the geopolitical context of where these things come from. But then we also have to look at, well, how did they get to that? And we have two different terms that we need to, again, understand. They tend to be used interchangeably by most people, especially after COVID. You'd have seen a lot of press saying supply chain disruptions. We need to have more robust supply chains. We need to start bringing the sources of raw products back into our countries. We need to start doing the downstream beneficiation in our own countries. And this is what it's referring to. So the two concepts is moving your raw product from point A to point B, which is plane, train, and automobile type of stuff. But then also we're looking at the value add component of that. And this again now gets back to a lot of the things that you'll see happening, for example, in Zimbabwe with lithium, happened a couple of years ago in Indonesia with nickel, currently happening in Mexico again with lithium. Various South American countries are talking about with copper. So governments are now seeing a value add proposition in terms of the tax base. So if you're mining and selling a raw product, so you're not beneficiating anything, the tax that the government can levy on that in terms of export duties is reduced. So what we're starting to see in the world is effectively nationalization policies coming back into play, but also the end of globalization, so limiting of free trade between countries. There is actually a lot more trade restrictions coming into play internationally than there have been pre-COVID. Countries again are starting to limit how you can trade independently and internationally. It doesn't help that we've had situations like the current situation between Gaza and Israel, or the war in Ukraine, because we're now redividing the world into geopolitical blocks, and countries are starting to take sides. And part of the way to fight an economic war is obviously to restrict the flow of metals and minerals to other countries. But we also talk about supply chains a lot. But when you start looking at it in a little bit more detail, this is a study done by Screen, a really interesting website to go to, which is a European think tank who started to look at, well, how is the supply and demand of metals influenced in terms of, well, primary exploration versus recycling. Now, there's a number of things which, again, when you start analyzing this diagram, start becoming quite interesting, because on the face of it, yes, it's a very, very complicated diagram. So we're not actually looking at a supply chain. You're more than likely looking at a supply web of things. But what we can start teasing out is some of these other aspects. So one of the things that people talk about a lot is the whole concept of a circular economy, and we can go and recycle things. We don't actually need primary raw metals and materials anymore. Once we build up a base load of raw metals and materials into our supply chain, then we can have effectively a circular economy. So once you've finished with your iPhone, you recycle it, the metals and minerals in that iPhone come back into the system, and they can be reprocessed or recreated into a new iPhone. We don't need to start mining primary raw materials from the earth. Now, again, that sounds really great until you start getting into some of the nuts and bolts of that. What tends to happen with the metals recycling process, and again, it's a whole discussion which there's not enough time, or I'm sure interest to get into it in that much detail. But what tends to happen is the amounts of the specialty metals, so things like indium, germanium, lanthanum, the lanthanides, are present in very small amounts in your high-tech goods. So the logic of saying, well, we're going to be able to recycle all the indium in the system or the scandium in the system tends not to really happen because of, one, the very small amounts, and two, a lot of the times they're in alloys. So when you try to reprocess an alloy, you then will focus on the primary metal that you're interested in, and it is the remaining metals tend not to be recovered. Okay, again, it's a very, very simplified explanation of what's going on. Where there has been a lot more progress is in the recycling of lithium batteries, not only for its lithium content, but that is the primary goal of lithium batteries recycling, but also things like graphite and copper. But also what does tend to happen in recycling, what's referred to as black mass, which is what happens once you've dismantled the lithium battery or lithium-based batteries, is again, you're not getting a full load. So if you've got 10 grams of lithium in the black mass, you're not going to get 10 grams of lithium out. We all know this is just part of metallurgy. So we're always going to end up having to have primary exploration and primary mine development. But what we're also starting to see a lot more of, and this is very true in trends that you were seeing in terms of especially the EU and West, or the global North, for want of a better expression, is a lot more dependence or a lot more regulation in terms of ESG coming in. So take, for example, Serbia with the Jadar deposit that has been scrapped. And even though Rio Tinto would like to get it back on board, the general consensus coming out of Serbia appears to be that, well, Jadar is probably not going to get developed, or if it does, it's not going to be anything like what we originally anticipated it to be. Portugal has effectively canned all its lithium operations at the moment, even though the Prime Minister is very pro. He's just been indicted in terms of corruption. So effectively, any lithium mining or any other mining in Portugal is probably not going to happen in the medium to near term. And we're seeing similar things happening in other European countries, and especially those countries in Europe, the Baltic states and the Balkans, where traditionally did have a mining industry, and that's not happening. France is struggling to get a large lithium project online because, again, while people say they want to go carbon neutral and they want to go for a green transition, at the same time, there's a lot of pushback from local populations saying, yes, they want to go green, yes, they want carbon neutral, but no, they don't want to have mining in their backyard, and they're quite happy to push it out to other developing nations and or nation states. So looking at this, yes, the takeaway is that we're always going to really need primary exploration for metals and minerals. We are going to see a change in terms of the global demand that we need. So yes, copper is always going to be one of the big ones, as we can see with the development of all the operations currently in the DRC, as well as Zambia. But of course, that then brings pushback from the governments, because with all that interest in copper, they are going to then start wanting to, or they will start anticipating seeing more revenue flowing into the government coffers. That will then probably change with governments either wanting higher taxation occur, then whether by the way of royalties or the direct taxation, or companies to do direct investments in communities, which is what we've seen, for example, in Ghana with gold operations, where governments have effectively said, well, a mining company is now a lot more responsible for the local ESG aspects than the government actually is. So again, while we can start looking at this and saying, yes, we've got a great future in terms of primary metal extraction, we need to be very cognizant as explorers and geologists that there are a whole load of other aspects at play in the global sphere, which may or may not make that metal or the commodity that you want to go and explore for as attractive as what you thought, or it may mean that the destination that you're targeting may not be as interesting as what you thought it was going to be because of increased government regulation or taxation. So how do things travel? Well, again, this is when we start getting into the supply chain aspect of things. Where do metals and minerals go to? Now you can see, for example, South Africa is a primary exporter of raw materials. This is something that for at least 20 years, the ANC has been saying that South Africa needs to beneficiate and upgrade before South Africa exports. because there's a very low revenue generation in terms of taxation that the government can levy for this. The problem comes in South Africa, as we all know, is that to do any metal beneficiation, you need a consistent supply of power and you need cheap power. So if you're not going to get that, trying to beneficiate metals within country is not going to work particularly well, and you're probably going to be forced, as in the case of South Africa, to export to other countries where the beneficiation will occur. So South Africa is effectively losing out in terms of the value chain component of the metals and minerals that South Africa is richly endowed with. You'll see in the map, there's a whole lot of countries which are not shown. So if you go to resource trade, you'll see that they have used it on public domain information. So things like trade from Zimbabwe and Zambia and stuff is not done. Also, this diagram is looking at specialty metals, which, sorry, I forgot to say. So specialty metals is, again, pardon me, one of those new terms that you're going to be coming across. So specialty metals is analogous to critical raw materials, but it's more specific in terms of the and byproducts that you start seeing. So we'll cover things not only the PGE group, but it will also be things like indium and lanthanums and rare earths. So it is a bit of a mishmash, so it's not too clear. But also remember or be aware that when you start getting into some of these specialty metals and minerals or minor metals and minerals, the market is very opaque. So you can't just go to the London Metal Exchange and see what is the spot price of lanthanum today, or what is the spot price of indium. It doesn't happen. A lot of that market is controlled by traders or metal traders. You do have the larger companies, obviously, like the Glencores and Trafigura, who do it. And again, they tend not to be that transparent. But specifically, a lot of it is controlled out of China, specifically in Shanghai. So again, you're not going to start seeing that market transparency coming through. There has been a lot of moves to try and regulate the market. But again, there's always a lot of kickback, either from the metals traders or in many ways from the Chinese government, because there is a control over the supply and demand of metals and minerals. Now, those of you who've been following the news would have seen that not only has China started to limit the export of various graphite components or graphite products, it's also started to clamp down on the export of gallium as well. And again, gallium is one of those high-tech metals which you need in terms for things like computer chip manufacturing or lasers and other high-tech equipment which militaries need to use or militaries use. One of the things I do want to point out, though, is this little interesting trade route from Myanmar to China. Now, this is one of those more interesting anomalies that you tend to see in the metal space, where Myanmar actually exports up to 30% of, or rather China's dependent on Myanmar for up to 30% of its rare earth imports. Most people are of the opinion or believe that China is totally independent. It's not. So Myanmar and China do have a very strong relationship in terms of raw materials as well. So you shouldn't just assume that because of what you see is what it's going to be. There is a lot of underlying relationships as well, which are worthwhile understanding and knowing. But we also start dividing things into upstream and downstream. So the upstream side of things is our exploration and mining aspects. We then move through the value chain and the supply chain into what's referred to as downstream. So this is where products are made and manufactured. And this is an example, as you can see, of copper mining, and a good indication of where copper metal goes to. So a lot of it goes into construction and infrastructure. So again, if you're going to be mining copper, yes, it's going to go into EVs, but chances are that copper will actually end up in a building or in a power line supplying electricity to a house or to a factory. But it's understanding who those end users are, because a lot of those end users will be very critical in terms of where your market is going to be sitting. And a lot of companies now, especially, well, China, obviously, but India, South Korea, and Japan, as well as some of the larger manufacturers like Airbus Industries, Ford, Mercedes-Benz, are trying to have what's referred to as a vertically integrated supply chain. So the country or the company will then enter into a direct relationship with the mine. So all the material mined will then be sent through to Ford or to Chrysler or to Airbus Industries for the use in the products that they're making and designing. This leads to a whole lot of other issues, which unfortunately we don't really have too much time to discuss. Maybe we can get into it in question time.
Speaking of
What?
time, 5 minutes. Mark.
Yep, no, I'm aware of that. So speaking of that, well, then what happens when supply chains get disrupted? So Fisa, I've actually got very few slides this time, so it's not my normal. So what tends to happen when supply chains get disrupted is they have massive economic impacts. Now, remember what I said, that things like germanium and indium and iridium are used in very small amounts. The problem is that those small amounts go into products which are high value. So if there's a disruption in the supply chain, those high value products cannot be manufactured, and it can lead to massive losses in those downstream industries. So this is an example from the car manufacturing industry. It's a bit dated, but it does show when, for example, when there was supply chain disruptions during COVID, there was massive losses in terms of the car industry in the States because they could not get some of these specialty minerals and metals into the country for use in manufacturing. I've mentioned several times, okay, well, we're talking about byproducts. So this is a graphic screenshot of all potential known lead zinc deposits in the world. Now, for those of you who are not aware, most of these weird and wonderful names actually come as byproducts from lead zinc. It's not always the case, but a big chunk of it is byproducts from lead zinc manufacturing and mining. Now, what does the economics of lead zinc look like? Well, again, very much dependent on supply and demand, very much dependent in China. For those of you that are not aware, China's economy is slowing down. The state has a limited steel production in China, which has had a knock-on effect on everything else. So what we're now seeing is a reduction in the zinc price. Admittedly, this is out of date. The current spot zinc price last time I looked was $2,550 a ton. So it's currently we're sitting at a lower level than what we have in the last 3 years. The implications for this, well, for example, Boliden has shut down its Irish operations. So Tara mine is on care and maintenance. So again, we're not necessarily seeing all these buying co-products coming into the market. And because most of these buying co-products are processed and extracted in China, which has the largest concentration of lead and zinc smelters in the world, again, you're now seeing potential supply chain disruptions potentially coming through into this, which will mean the prices in those very opaque markets will start going up, which will lead to a knock-on effect. Now, does that mean that you should be starting to look for a lead zinc deposit? Well, that would be up to you, but we need to then understand the other issues that we've got. Now, how do we go about this, or how have countries went about doing this? Well, they look at a number of ways to try and limit where they get the metals and minerals from. One of the things is referred to as multi-sourcing. So you try and have trade agreements with multiple countries or multiple companies. Now, a very interesting study was done several years ago by one of the many state departments in America, where they started looking at the rare earth supply chain. They assumed on first glance that they actually had quite a dispersed supply chain, and it was a pyramid shape. So they had a lot of suppliers going up to one or two end products. What they did discover, especially when they're looking at what's referred to the Dinky suite of rare earth elements, so dysprosium, indium, niobium, and yttrium, that it was actually a diamond shape. And when they started investigating, they discovered that they're actually beholden to one or two Chinese suppliers. So it wasn't as robust as what they thought. So again, why America started reopening Mountain Pass, for example. Nearshoring is also a way. So you start talking to friendly neighbors. So America and Canada, or America and Mexico, for example, having stronger trade relationships coming through. Starting to build up inventories or stockpiling. America is rebuilding its strategic stockpile. It started dismantling it several years ago, but now under the Biden administration, America is starting to stockpile massive amounts of what they consider as strategic raw materials. Europe is now discussing strategic stockpiling, and there is a number of high-tech companies who very discreetly in the news have been talking about stockpiling of some of the metals that they need and are critical to their economic activities. Now, there are sometimes unexpected consequences. So the IMF did a study and said, okay, great, if we start going nearshoring or friendshoring is the alternative name for it, and we stop international trade, well, what is the overall economic impact? So in their study, if we were to friendshore, if every single nation was to friendshore and not have international trade, overall, the IMF indicated that we'd see a reduction in the global economy by about 5%. But if you look at individual economies or individual trade groups, it could be quite significant. So India, who is now the largest country on earth in terms of population, would have a really negative impact on their economy. And Russia, for example, would have a very large impact. Again, taking into account Russia, for example, is a massive supplier of nickel and PGEs to the rest of the world outside South Africa and Zimbabwe. So we do have a number of things that will come into play for this. So if you decide to go exploring in Africa, well, again, this is from BGRM. This is their map of known critical raw materials. Going throughout Africa, you can see Central Africa is relatively unexplored, again, for very obvious reasons in terms of geopolitical risk. But there's a lot of places you theoretically can go and explore for some of these materials which are critical to the world economy at the moment. However, we need to remember what's referred to the midstream, where manufacturing occurs. So no matter what you do, chances are that at the end of the day, you're going to end up having to talk to the Chinese, or at least understand how the Chinese markets are operating, whether you're having lithium, which China's basically just secured the supply of all lithium coming out of Zimbabwe, for example, rare earths, or any of these other things. As I said, lead zinc, they've got the largest concentration of lead zinc smelters in the world. So again, if you're starting to look at this type of stuff, you need to be very much aware of it. The other thing, if, for example, you do decide to invest in lead zinc, be very much aware that a lot of these specialty metals actually are considered as being deleterious in the smelting process, and you as a supplier will end up paying penalties if you have high concentrations of those metals in the ore that you're sending to a smelter. So it's not like a case of you've got a high indium content that you're going to actually make money out of it. You could actually end up in the situation where if you've got high indium, you're actually going to be in a worse situation than if you had a low indium concentration in your ore going to the smelter. So understanding the smelting contracts becomes very, very critical, and who's processing that material. Other things that we are seeing over time, and I'm almost done, Sfisa, is that as we are progressing and opening up, we are seeing, again, unintended consequences. So this is a map, and again, it's really great website to go to, showing the level of deforestation that has occurred over, I think, the last 10 years in the DRC. And effectively, the implications of the deforestation is because there's a lot more interest in mining and exploration in the DRC and Zambia. And because of the access routes, and because of more people, and because of more money going into the system, there is a larger number of people moving in who then need wood for cooking and building and living areas. So there is a knock-on effect of this. Now, how this is going to start playing out, I don't know. But again, it's just something which is now getting monitored by NGOs across the world, that, you know, there's, at least in some people's opinion or perception, there is a direct relationship between deforestation and exploration and mining activities. Now, we need to understand that, and at least be aware that these are some of the concerns or some of the perceptions out there in terms of activities that we as geologists get involved with. So my final slide. So yes, you may be tempted to go and look for one of these really interesting specialty minerals. You do, however, need to make sure that you are going to have some degree of economic viability. I haven't missed the other E. In the latest discussions at CRISCO, the eventual is getting dropped out of it because of a lot of zombie projects in the market, which we all know about. So people have a project and it just seems to drag on and drag on and drag on with no eventuality of ever coming into production. So there's going to be a lot more focus now on, you know, when you're going to start bringing these projects into production and move them up the value curve. You need to understand your you need to understand your metallurgy. Are you making byproducts or co-products? What is the market for that? How easy it is to process. I mean, people talk about rare earths. You need to understand the metallurgy of rare earths. You need to understand that certain rare earths are more valuable than other rare earths. So if you have a deposit which has got a lot of light rare earths, is probably not going to be of too much value. But if you've got something which has got high neodymium or dysprosium, it is something that people may be interested in. But each rare earth project has its own metallurgy, and you will probably end up spending a lot of time and money trying to figure out the metallurgy and the best way to process your rare earths and to get it out. Other thing is, a lot of these can be potentially carcinogenic or environmentally damaging, and you have very few options in terms of processing except China at the moment. Do you make your concentrates? As I said, there's countries like Zimbabwe who will not let you export a raw material. You have to export a concentrate, so whether it's a carbonate or a hydroxide in terms of lithium, or if you're going to beneficiate it, do you have sufficient power? And I should probably add water, because there's again a lot of emphasis on water and the use of water in a lot of these in terms of looking for some of these CRMs. For example, one of the kickbacks in France against one of the large lithium projects is the amount of water that project is going to consume when it's producing its hydroxide. And there's a lot of feedback in terms of that from the local population saying, but this is an agricultural area, you're going to be using all this water, how's it going to affect the water balances, how's it going to affect our water wells? And I'm sure this is going to lead nicely into something that Camille is going to be talking about during I think Camille's talking tomorrow. Anyway, that's me, finished, all done.
And yeah, you had me fooled at slide 8. I thought you had 2 more, but I let it slide because you're not here to feel my whip that I have for the speakers, but also you're a friend of the society and also a great source of information. So I let that one slide. Speaking of sourcing, multi-sourcing CRMs, I'll allow a question quickly for Mark before tea time. Okay, there's a question coming.
Thank you very much. Thank you very much, Mark, for the informative and insightful presentation. My name is Stanley Smart and I'm a student at Wits University. So my question is based on the PGM market. Recently, we've seen the decline in the commodity price of PGMs, and that is affecting the PGM industry in South Africa. So, and the last time I checked, South Africa is it produces 75% of PGMs of PGMs in the world market. So how is South Africa still a price taker, not the other way around in terms of pricing the commodity? I don't know if my question is clear. Thank you.
It is. Okay, so the first thing, if you want to see some really good stuff in terms of platinum supply chains, go and look up SFA Oxford. Steve Forrest and Associates Oxford, they've got some really, really good stuff in terms of platinum supply chains. It really boils down to supply and demand. For those of us of a certain age, we will remember when working in the platinum mines was not the place you wanted to be, because platinum back in the late 80s, early 90s was worth even less than gold for a while. One of the reasons why platinum increased is because of the need for catalytic converters for diesel and petrol driven cars. If we are going to move to a full EV driven society, then obviously there will no longer be the same demand for that. If you've been reading some of Neil Froneman's comments recently, Neil is saying, well, if we are going to be doing that and we're moving to a hydrogen-based economy, then yes, there's still going to be demand for platinum. So it's going to be one of those things. At this stage, it's not clear which way we're going to be going in terms of moving green, in terms of transportation. So if there's a major move to hydrogen power, then yes, the future of platinum is probably a lot more positive. If there's a major move to battery-driven vehicles, then chances are the future of platinum is not going to be as positive. So at this stage, it's very much in the hands of people like the World Economic Foundation and the UN in terms of where they're going to see those markets developing. If you start looking at the big automobile manufacturers or the car manufacturers, a lot of them are splitting the bets. So for cars and stuff, they're going to battery driven, and for larger transport like trucks, they're tending to move towards hydrogen. So again, it depends really on which way the market goes. So I guess the way I can't really answer it, it's very much up in the air at the moment. And if I was working in a platinum mine, I guess I would hedge my bets and start looking at learning as much as I can. So if things don't go well in platinum, I can upskill myself and potentially move somewhere else.
Good morning. So now my name is Maria Combrink. I'm a principal consultant with ERM, and my specialty is data. It's no secret. I love data. And what we do at ERM is we offer you a complete value chain along the whole value chain of mining, everything from exploration all the way to closure. We can assist you with permitting, programming, data management, mineral resource estimation, or anything else that you need to slot in along that value chain. Okay, so just a quick overview of what we're going to just discuss today. So in anticipation, so that you can get your questions ready. I'm just going to start off with a touch on what is industry best practice as we know it currently, then the spirits of the code, and governance versus compliance, and then planning for success, and what will happen if your governance and your data is less than desirable. So, as we all know, everything starts with data, and data that is loved tends to survive. And that is the aim of my role, is to make sure that whenever you go out and you gather data, that data manages to survive as long as the company survives. Even when you sell it on, it's still there. So firstly, why do we have industry best practice? So as most of you are aware, the Bre-X scandal and the Busang mine site in Indonesia in the 90s, there was significant amounts of gold found. And what happened was that the company then listed on the Toronto Stock Exchange, and initially it was less than $1, and it ended up at more than 286 Canadian dollars per share. And then that entire project was then capitalized for over 6 billion Canadian dollars. If you are interested in this, just as a side note, GeoHug, which is the Humans United with Geology, are presenting a webinar and talk on this whole Bre-X with some rural players today, if you want to look at the scandal of intrigue, danger, slander, and greed. So in the wake of Bre-X, there was a number of lawsuits, angry investors, and obviously Bre-X went bankrupt. There was dramatic trials, mysterious deaths and murders and suicides, and also a Hollywood movie. But excluding that, it has also given rise to different reporting codes. Among others, the NI 43-101, which in its spirit is to protect investors from unsubstantiated mineral project disclosures. So why did this happen? Because what happened in the whole Bre-X scandal was it was found that the assay samples were salted. So there was gold added to it, and it was actually shavings from gold jewelry. But nobody could say where along this assay process it was actually added. And this resulted then in our best practice. So just a quick overview, I'm focusing purely on the exploration side before we go into mining in terms of the best practice. So when we start with our exploration planning, we will look at this is where it all starts. And we'll have to say, even if we're exploring in a specific country, will we also be listing in that country, or will we be listing in another country? So when we start planning our exploration project, we must already keep in mind of the reporting code that will be relevant for it. Then we will move on to how do we get the data, and what systems will be used, what systems will be implemented, and will it be implemented consistently? Then the geological records, do we have the bare minimum as required by any reporting standard? So do we have collar surveys? Do we have unique collar ID numbers? Do we have the drill type? Do we have core diameters, lithology structures, etc.? Then the RQD and SG is also, they're also very important for looking forward. When you start looking at how am I going to develop the site, or how am I going to apply this in terms of my mineral resource? So, and then we have to know which methods were used. And then looking at the core yard, how was it stored? How is it cataloged? Can we still retrieve that core? Is it still viable? Leading into the sampling procedures. So are we consistently sampling the same way? How are we cutting the core? Are we making sure that there's no contamination in that? How are we allocating sample numbers? What is the CRMs that we are using? What is the documentation and the sign-off process associated with this? Then going into the sample dispatch. So sample dispatch will be the collation of the samples, the controls in place to make sure that there is no swapping and no salting, and also to make sure that your samples are secured as it is being transported from the core yard to the lab. So at the labs, we have to know which lab it is it an accredited lab, what procedures are we using, and also if we are going to select a referee lab. Then our CRMs, in this case, not critical minerals, in this case, standards. So what standards are we using? Are the standards that we're using actually speaking to the ore body that we're investigating? I can't have a platinum standard when I'm looking at a highly sulfide gold deposit, for instance. My standard must speak to the expectation of my ore body. Then lastly, in terms of the assay and the sampling, where is the results handling? How is it handled? How are those results passed over to the database? And then the database management and software. So has that database got in the correct validations, triggers, and constraints so that that data that goes in is not garbage? So when you start using the data, is it actually telling you what is happening? And does that conform with industry best practice? So, and then finally, when we look at the statistics and the graphs in our QC monitoring, there at number 12, it must be consistent statistics, and it must be consistent graphic layouts. You can't just use statistics that will best represent your worst case results. Why is this important that we look at industry best practice? As you are all aware, the mineral resource and mineral reserves reporting codes across the globe are currently in various stages of being revised, and this is to include some ESG metrics. So why is this important? Because embedding ESG concepts like biodiversity, protection and management, stakeholder engagement, decarbonization, pollution prevention and management early on will save you a lot of tears for later. So, for example, discussions with local authorities and landowners and local communities are required before you even go out and get that exploration license. And you must then further have an understanding of the implication for the environment and the social context in that setting where you are exploring. So little things like, is it a protected area? Is there an endemic species there? And what would the water use in that area be like? So ESG performance has become a defining feature in the marketplace that is being used to differentiate preferred investments. There is a wide recognition that the approach taken by mineral companies to accommodate ESG requirements in the reporting codes needs to evolve. So this is important because how you treat not only your geological and geotechnical data, but also how you start looking at your ESG data right from the beginning will be a defining feature that might place you as a preferred investment for investors. So if you think about it, when you send out your exploration geologists into the field to map or grab samples for that very first time, they are often the very first contact the community and future stakeholders of that area has with your project. So if you arm them, your field geologists, with the correct information, they will be a good face of the project, and they will set a good tone for future engagement. So that leads us to the codes and the spirit of the codes. Because we're all familiar with all of the codes, I'm not going to run through them now. What I do need to highlight here is that if you are a qualified person for any of these codes, you must declare whether the data has been, that was disclosed has been verified, including your sampling analytical data and the test data that underlines the information contained within your disclosure. And you also have to do a description of how and where and how the data was verified, and also any limitations or future failures of said data sets. So we're all very well aware that great data starts in the field. So that's the sampling, acquisition, the techniques, and the field data capture. And I see a lot of my clients, it's very common to spend millions of dollars on drilling, and then only to have it captured on paper logs or Excel files, and not looking after that data. So I like this slide because Brent Cook states here, so this is the life cycle of a junior explorer as Brent Cook highlighted in 2010 already. So he says, success for speculatory depends on, 1, investing in a management that is intelligent, honest, and financially committed. And 2, properly assessing a property's potential to host a major deposit as early as possible. So if we look at this life cycle of a junior explorer, we'll see this is the normal curve that it will take. So 4 to 5 years for the concept phase, going into your exploration phase, which becomes a bit of a critical stage here, because that will all culminate from the information that you've gathered based on the data. So without good governance, this speculation curve can actually extend and become more or less like a cliff, because nobody's going to trust what you say is true and valuable. And that will increase your exploration time and your exploration cost. So traditionally, the reporting was based only on geological data and associated assay data to speak to the mineral resource and reserves. And this was then followed by due diligence. And the aim of the due diligence is to highlight any red flags. So are there any technical gaps, bit of financial opaqueness? Was there some lack of social engagement? And based on what that due diligence find, it will give you a possible outcome. Yes, you can look at this project, but you'll have to proceed with caution. So you'll have to take an approach that's phased and see how we progress along that. Or don't go there. There are some fatal flaws contained within this project. Or go ahead. It's perfectly fine. And the way reporting aligns with the different codes is to assist with the possible outcomes and evaluation of this project. So basically an informed decision based on data. So when we look at the data, we have to start looking at the reputation of that company or that competent person or that manager that was responsible for the data gathering, because that will also start to highlight the risk tolerance of that company or that manager or that qualified person. When it's evident that we look at this, the governance is set by the company's leadership and will speak to the culture of the company as well as the approach to risk. Which brings us to a quick overview of governance and compliance. So data governance is a subset of governance where we look at data management to ensure that we have proper policies and procedures in place, that we end up with good quality data that's available, it's got good integrity, it's secure, it's usable, and mostly it is transparent. Governance is an inside focus. Governance is set by the company itself, and it speaks to the long-term performance of the company. So it is set in by your executives, your board, or alternate inside stakeholders. And should you not comply to governance, it will result in termination or something within the company, not necessarily from an outside source. However, compliance speaks to a legal requirement that confines you to a set of law. And the consequences will be legal action, fines, or penalties. So that's ruled from outside. So the important thing when we look at our data is, as the reporting landscape is changing, there are new metrics that are also being imperative. That's also imperative to be included right from the start. This is excluding geological data because we're all very well versed in that and how to look at it. But by looking at future trends, we have to look at what the value add will be. So we have to be aware of greater objectives and goals at each stage of the project. So what does that mean to be planning for success? If you want a result, you'll start off with what is the goal. So as you move through the different phases of your exploration or mining or production or closure, you'll look, what are my goals? Where are we heading? What do I want from it? How do I get there? And then the strategies and the measurement will solely be based on what kind of governance and data do you have. Because if you have strategies in place that you can measure and target, that you can actually speak to, you can reevaluate based on the results that you get from what you measured. If you cannot measure it, you cannot say, did I reach my goals? So even in 2006, it was evident for Berry and McCarthy that when you look at the beginning of your project, a third of your risk will be from non-geological inputs. But what's happening now is as you progress down your project timeline, you'll find your geological risks will decrease and your non-geological inputs in risk will increase as you move along and in getting to establish production in that. So in today's rapidly evolving business landscape, transparency has emerged as a powerful tool for organizations to build strong and lasting relationships with their stakeholders. Whether it's the customers, the employees, the investors, or the wider community, stakeholders are increasingly demanding transparency from companies. And what does that mean? So if you are transparent, you build trust, which results in accountable and responsible reporting. And if you're accountable and responsible, you will end up with ethical decision-making, which will ultimately give your company that competitive advantage. And because you are following all of those steps, you will slip into regulatory compliance in an unassuming way. And that is the whole center of the spirit of the reporting codes, to be transparent and give people the best data information as possible. So what happens, I'm not even going to look at you. So what happens if your data governance is less than desirable? So basically, contract transparency is a key component of good mineral resource governance. It has been found that there is a very strong link between the level of governance and the degree of social progress that's enabling mining companies to mine and progress within that area of totally mining dependent countries. So the higher the quality of governance, the stronger the socio-economic progress observed. So what is contract transparency? it's the public disclosure of contracts and licenses that explain the rights and obligations of all of the parties involved. So that would be the exploration, the production, any amendments or supplementary agreements that might be there, like the local development plans, as well as what is expected from the local communities. So these agreements provide the specific terms for which the mineral resource will be explored, exploited, and who will benefit: the government, the citizens, the local community. And this is one of the reporting prerequisites for members of the International Council of Mining and Metals, the ICMM, as well as the over 50 countries that have signed to the Extractive Industries Transparency Initiative, which basically says these are the rules of governance when we come to your area to explore, and this is how transparent we are going to be and how we are going to go about our reporting. So just I've got 4 slides left. So just 2 countries that you can see where governance was not great. For instance, in the Geita district of Tanzania, what happened was the company said, we are going to do all of these wonderful things. And when we actually look at what was reported and what was done, your corporate social responsibility programs that was reported on was actually mining development infrastructure. It was roadways and power stations and everything that benefited the mining and not the community. And this resulted in social unrest and employees striking because reporting was ambiguous, misleading, and omissive. So just BS, business speak. And then very recently in September 2023, the Democratic Republic of Congo, the government suspended over 20 mining licenses. And they said it's because companies had not signed the documents related to social and environmental commitments to local communities. So if your governance is not good, you're leaving yourself open to issues such as this. So for instance, in this case, the one company that was really influenced was Eurasian Resource Group, but they have good governance. So they were able to complete the cahier de charges to say that we comply to your specifications, and they have now recourse to actually take this further internationally. So ESG is shifting from loose guidelines to mandatory obligations around reporting and standards. So it's international standards as well as jurisdiction-specific standards as well. As we know, CSR is voluntary and you can't measure it. However, ESG have metrics that can be measured. It's future-focused, and it's starting to play a pivotal role in investment decisions. So what does this mean? When we look at the EY census of what people are concerned with, for 2024, it's ESG. And it's exactly the same in 2023. It was also ESG. But if you look 10 years back, ESG was there, just in different forms. You're looking at social license to operate. You're sharing shareholder benefits, your water and energy. So those are all speaking to your ESG terms. So when we look at it further down the line, these are the ESG factors that's under most scrutiny in 2024. And aligned with this is how the reporting codes will now start looking at this. So it won't be reinventing the wheel. It will be more of an integrational approach to the Table 1 as you already know it, with extra reporting requirements. Thank you.
Morning, everybody. Yes, I'm Nico Denner. I'm the owner of GEMX. We're a small geological consulting company based in Middelburg, Mpumalanga. Mine involved exploration, geological modeling, reporting. Do a lot of work in the coal industry, as well as some other minerals like manganese or anything related to the bushveld. But I love coal. I'm passionate about coal, so I will speak about coal. Nobody else wants to speak about coal. Unfortunately, people don't realize we need coal. We've got abundant amount of coal all over. If you like it or not, everything around you in this room has got some coal in it, some sort of way. Still a long way for us to go. There's a lots of transitioning, what they call happening in the world. Unfortunately, if you look at the consumption of coal worldwide, this year would probably be the all-time high, and it will probably continue in the future. So it's not something we can wish away. It's not something that's going to disappear, and we need to work around that. So I'm just going to touch a bit on the coal. I'm going to talk about Botswana. Botswana had a big, call it boom in exploration in coal in the early 2000s. A lot of drilling, a lot of projects. I've been involved in a lot of those projects myself. Everybody was proving up these billions of tons of deposits. Unfortunately, nothing could become a reserve due to numerous things of markets, logistics mainly. So it basically died off and nothing happened. And then things started to change recently. So I'm going to touch a bit on that to see what's happening at the moment, where it's going, and a bit about just the history of the coal in Botswana. So a bit of coal, the World Coal Association. Oh, while I'm mentioning on this, I'm also executive member on the FFF Carbon Society, which used to be the old Fossil Fuel Foundation. That's been revived. We had a big conference in Middelburg last month on coal, world-class speakers. If you want to become involved or want to know more, or even follow the conference, the whole video link is on the FFF Carbon website. You can access it. You just type in FFF Carbon or even Fossil Fuel Foundation on Google. It will take you there. World Coal Association also gave a presentation there. Lots of interesting facts. Go and listen to it. Educate yourself. Learn about coal. So coal is used not only for electricity. That's a bit of a misconception. So it's still contributing 22% in the world. 70% of our steel is reliant on coal. But we can clean up 2 gigatons of coal carbon emissions can be cleaned up now if there's funding. So, but nobody wants to fund any coal. So there's a big improvement that can be made just on coal in the world. But it's a critical commodity. It affects our daily lives. It's got a lot of industrial use, steam coal, coking coal, coal to liquids. Think about Sasol, plastics, chemicals, fuel, diesel, high-tech materials, carbon fibers. The list can carry on. We can do a whole day to talk about all the products. It's a lot of research going in on new coal products that's high-tech, that are needed in our daily lives. So 30% global electricity comes from coal. Like I said, 74, 50%. It's big numbers. A lot of products, even from downstream processes after coal has been burnt, fly ash, slag, gypsum, activated carbon, carbon fibers, silicon metals. So if you look at the graphs, and this is from Dr. Lars Chernyshko, he written a book called The Unpopular Truth. It's a very informative book about electricity and coal and renewables, lots of facts that people don't want to talk about, that politicians are hiding. You can go and read that book. It's very interesting. But you can see the percentage of coal in primary energy, 27%. This is in the world. On electricity, 36%. If you look at the primary energy, like I said, coal is used, but there's coal used for heating, building, transport, industry as well. That's 60% of the use. So there's even more industrial use of coal than only generating electricity. And it's very difficult to get rid of that portion because we need it in our daily lives. If you look at again, this coal takes up 36% of electricity generation worldwide. And if you look at investment, where renewables, wind and solar is 8%, it takes up 45% of the capital investment at the moment, where coal only gets 19%. So that's very imbalanced at the moment. Let's go back to Botswana. So history of Botswana, coal consumption, production. Mainly Morupuli coal mine was the first mine to open, and it was only opened to supply coal to the power station. So supply and demand balanced out all the time. This is going back to the 1980s. And there was a bit of a change from 2010, where the production went up and coal consumption went a bit lower. And the upward trend in production was mainly due to exports and other markets that they started to access. This is just a graph up to 2022, and you can see production is steadily increasing in Botswana. So Botswana Energy is not a highly industrial country at the moment, and not a big need for electricity. It's got an installed capacity of 993 megawatts. It's one stage load shedding. That's what they're producing in Botswana at the moment. But they sit with over 200 billion tons of coal resource. So why Botswana? If you look at the economies of Botswana, it's a very stable, secure investment country. It's got the highest GDP in Africa. It's very stable, low tax regime, stable labor market, and it's expanding now in the export and the rail infrastructure, no foreign exchange control. So it's a very stable country to invest in. The coal market is still very small. Like I mentioned, Botswana sits with over 200 billion tons of coal, where South Africa is around about 50 billion tons. If you look at the resource base, it's currently only 2 operating mines in Botswana. It's the Morupuli coal mine and the Masama coal mine owned by Min Energy. Power generation 7 to 100 megawatts, but they plan to double that in the next 6 years. So there's things happening there. Botswana is also, in terms of the SADC region, is very centrally located, which is to its benefit. And they can very much easily export coal and energy in terms of electricity to neighboring countries. So yeah, just to summarize, 200 billion tons. They've got high quality resources. They also need to diversify. They're dependent on diamonds. The government also bought into the coal. And they also want to expand the other commodities, like, for example, copper, that we heard of at Tau as well. So part of the reason. So a bit of geology. If you look at the Karoo supergroup in Botswana, if you look at the country, 60% or more is covered by Karoo rocks. So there's enormous potential in terms of exploration targets. The main coal-bearing areas I've highlighted here, it's basically in these yellow areas, up here towards the north, towards Morupuli. Morupuli is down here, up to Sorowe, and at Mamabula, just near Gaborone. So most of the areas are situated on the eastern side, very close to South Africa. That's also where all the infrastructure of Botswana is sitting. We've got the railway line, the main highway going north, Francistown up here, Palape, Gaborone. So that's the main areas where we focus on the coal. There's mainly 5 big players or developing players at the moment in Botswana. And I'm going to run through each of them to tell you the story. Remember what I said in the early 2000s, there was lots of plans and ideas and nothing came about. But I'm going to talk about Morupuli coal mine, the Masama coal mine, Matla Resources, and Yindal Africa, and then lastly, Shuma Energy. So Morupuli coal mine, coal was discovered in, well, the mine was developed in 1973 already by Anglo American to supply coal to the Botswana Power Corporation. Eventually it was, they disinvested and it was transferred to the Botswana Diamond Company in 2000. And eventually De Beers sold their share to the Mineral Development Company of Botswana. So the company is state-owned. That's what it's all about. The state owns the company and they're growing it now, big time. So the discovery goes back to 1930, where they intersected coal first time when they drilled, probably for water, similar to what happened at Grootegeluk. And Anglo American got the mining lease in 1966 and they developed the mine in 1973. And in the beginning, all the coal went to the power stations. There were 2 power stations back then, one at Silibi Piku and one at Gaborone, and that's where all the coal supply went. So they steadily increased the coal demand or the coal production according to the demand of the country. And in 1986, that's when the new Morupuli power station were built. And that's really when production were upscaled. And by the way, they sold coal for only 7 pula per ton back then to the power station. So if you look at the Morokwili coal mine history timeline, like I said, they started production in 73, Anglo subsidiary since 1970, and they carried on when the Botswana bought in. And interesting, in 2003, that's already when they started to export coal to Zimbabwe. Only the mine started off as an underground mine, drill and blast. So they only introduced the first continuous mine in 2004. And in 2008, they added the wash plant as well to further beneficiate the coal and to explore and provide coal products for the export markets as well. So it was a steady expansion. They increased in 2011 up to 2.8 million tons a year. In 2012, they started to provide coal to Namibia and also to the new power station that was built. And in 2013, export to the seaborne market. So that's where the coal is going. They managed to get the coal out of the country, supplying it to Europe and Asia and other countries. So it's quite a big area. They've got a 42,000 hectare mining lease. They've got coal of over 4 billion tons. So it's a significant resource that's been mined for a long time. So it started in 1973. Initially, they didn't produce a lot. You know, they started off with 32,000 tons annually. Continuous miners managed them to up the production, and they've been building that up in 2011 to 2.8 million tons a year. They expanded with the Motheo project, which was basically adding up open cast, and that was started off in 2021. It is operational at the moment, and that managed them to go up from 2.8 million tons a year to 4.2 million tons. So they are a significant coal miner in Botswana. So they've got a very ambitious plan now. They call it a number 1327. So they want to be the number one employer, which they are in Botswana. On the SEG, they're very, very much compliant. One thing about Botswana, with the government being owners of the mines, they look after their people. So it's quite important to them. But they've got the strategy to build up to from 2022 up to 2027 to mine 7.6 million tons a year. And that will equate to around about 3 billion pula. That's the type of money they're talking about. Significant economic driver in the country. So the 3 is for the 3 billion, and they're going to get to there in 2027. That's a plan. So huge production increase going in Botswana. One thing they managed to do, it's always constrained, is how do you move the coal out of the country? That was a limiting factor. They managed with good partnerships, neighboring countries. They established export routes now via rail through Zimbabwe to Maputo. Last year, they even trucked coal from Botswana to Namibia, Walvis Bay, to export coal to Europe. So the logistics are now moving. So if you look at the coal projects, as I'm going into the next one, so Morokwili is up here at Pelapi. The other ones I'm going to talk about now is the Masama project, which is just not very far from Gaborone, less than 100 kilometers. And then we've got the Mamabula coal field, which is neighboring to South Africa. That's Matimba, Medupi power stations. That's where Grootegeluk. It's basically an extension of the Waterberg coal field. So this is where all the other action is happening at the moment. So Masama, with the second mine to open in Botswana, 100% owned by Min Energy. The license granted in 2018. Remember, I talked about the whole exploration that went in the early 2000s. A lot of projects, but nobody could get a mining license. But then it started to change from about 2016 onwards. Markets opened up, new investment came in, and people starting to get mining licenses. They could get to a reserve level, and the investment came in, and new mines started to open. So it's granted for 25 years. It took them less than 12 months from granting of license to production, which is quite phenomenal, being really much a greenfields project in Botswana. Again, look at the numbers. They've got a resource base of 376 million tons. We haven't got those mines in South Africa at the moment. Life of mine over 100 years, open cast and underground. And they also hold the prospecting license next to it of 352 square kilometers. These are huge licenses. And for prospecting, for coal and coal bed methane. Now, I'm not going to talk about coal gasification and coal bed methane because there's enormous potential for that in Botswana as well. And that will also happen. So Masama, just a couple of key facts. Like I say, 376 million tons coal resource. They've got upside. It's shallow and it's thick coal seams, easy mining. They sell local and they export different size products. And the advantage, and this is advantage to all of these projects, where they're situated in Botswana, yes, Pretoria, Joburg, easy access to the Northern Cape lime markets and to the cement market in the Northwest. They are closer than the Middelburg, Witbank areas. So it's for them opportunity to supply the South African local market and to export. Mamabula coal mine, this is one I'm involved in personally. We've done the exploration work here. It's just 120, 150 kilometers north of Gaborone, up here, bordering to South Africa. They would be the third mine. They're busy with construction. They're fully funded. First coal would be out next year. The mining license was granted in 2021. And they're planning to do 100,000 tons a month open cast, export, local markets, South African markets. Very similar to the Waterberg coal field. This is the benches at Waterberg. At the bottom, there are definite coal seams within sandstones. And this is a similar coal seams we see in the Mamabula area in Botswana. And that's the target. Just to show, this is on Google Earth. This is a project. That's the mining lease area. Here are all the drill sites where we drilled recently. The plant construction sites, everything is being cleared. Transmission networks are in. The process is going. So they would be in production next year. The nice thing is here, when we drilled, we could increase the coal resource by 40% after the recent infill drilling, which is always nice as a geologist if you get involved in a project like that. Next door neighbors immediately north of them are Yindel. They call it the Mamabula Energy Project. They would be the fourth one. They're also busy with construction. They're going to open up 3 mines and they're going to sell electricity. They already got 600 megawatts approved by the government. They're going to build a mine, put up a plant, sell electricity to Botswana and supply another 300 megawatts that's also approved to South Africa. So that's where it's happening. They've got a resource of 2.4 billion tons. So endless supply of coal. Most of it can be mined by open cast. Like I say, it's all about electricity generation, but the coal seams also suitable for gasification. Now, Yindal in India has got experience in coal to liquids, coal to gas. So the idea is also to put up plant there to sell additional products from coal. So yeah, the coal to liquids thing will also come in. Last one, Shumba Energy. I'm almost done. Okay. This is back in 2016. Slides I took from them. That was the idea and the thinking back then. Shumba Energy. They've got lots of projects in Botswana. Billions and billions of coal all over the place. Up here north, towards the central areas, to the south. And a lot of these projects were drilled. And the whole idea of Shumba Energy was the opportunity for sustainable, affordable energy in SADC. And that's what coal is so important. Everybody needs cheap energy that's sustainable baseload. Coal can provide it. We can provide, Botswana can provide it for the whole southern region. So this was the vision back then in 2016 already. And that's happening now. Yindal's already taken a step, and this will happen because Africa needs cheap, reliable energy. This is what coal is going to give us. Botswana's limited in terms of export. They can export, but it's easy on the network. You export electricity, you don't export coal. So that's what's happening there. So they had a number of projects back in 2016. You see numbers like 300 megawatts, coal-based mine-to-mouth power plants, a number of licensing areas, shallow coal resources. Most of them were well drilled. And this is now in 2019, not long after. Shuma Energy enters into a liquid fuel partnership with the Chinese. It's going to happen as well. Coal to liquids. Think about another Sasol in Botswana. Botswana needs diesel. They need fuel. They import from South Africa. They can become self-sufficient from coal. They can sell electricity to the neighboring countries. So things are happening. 2023, energy projects, Sumba, they already started. They've got a solar project now up and running. And the next, it's quite a lot here, but you see 2 times 150 megawatts. I'm talking about partnering with Kibo Energy. We look at coal to liquids to be developed. We look at 600 megawatts power plant production, coal to liquids. It's all happening. So different way of mining in Botswana, things are happening, and we'll probably see, hopefully in the future, what I love to do, drill, sample coal, model coal, get these big resources proven up, get the reserves on the table, but with a different mindset than we had previously. It's all about industrial, it's about energy, it's about securing supply, it's about coal to liquid, coal to fuels. So I think Botswana's got a great future out there to develop the industry and become a big, enormous powerhouse for the whole Southern African region.
Thank you. Thank you for that. That was quite interesting. So with the Mosama coal mine, you mentioned the resource uplift. Can you maybe just elaborate more on that?
Just again on the Masama coal mine?
Yes, the resource uplift that was done. Can you maybe just elaborate more on that? How
Well,
was it done?
the one where we increased the coal resource.
Yes, yes.
Yeah, so what basically happened, the previous exploration phases that was done many years ago, there are different coal seams, which we call the D and the M seams that they target. And the previous geological campaign only focused on the lowermost coal seams and sampled them. But if you're familiar with the Waterberg coal field, we've got these interlaminated shales, carbonaceous shales with bright coals. So those horizons were never sampled previously. They drilled through it was quite shallow. Only the coal seams were sampled. So 2 things happened. Closer spaced infill drilling that we did, because the sub-outcrop positions of these coal seams were not very accurately defined with the previous phase of drilling. And in addition, the uppermost coal seams that were interbedded in the shells, we also sampled, and there's significant coal there. We're talking about coal thicknesses of up to 1 to 3 meters that's present that were never sampled. So they were never in the resource base, and we sampled it, we showed the qualities are there, and that was added to the resource, and we had better definition of the sub-outcrops, and that led to a 40% increase. So it changed the whole mine planning around in a good way. So that was upside, yeah. Yeah, when you do geology, by the way, if you're in a new project, sample everything. And that's the thing about coal as well. And a sample, yeah, you have to. Even if you don't know, just last comment is a thing about coal as well. Years ago, you were looking, for example, you target a CV that's got a 22 calorific value, megajoules per kilogram. That's economical. If it's a 18 or a 16, people were not interested. Economics change. With a 16 CV, you can make coal to liquids. It's about fixed carbon. It's about other elements in coal. So don't just disregard it. Sample it. It might be useful in the future.
Thank you very much for the opportunity to speak and to introduce Cameroon as a destination to a slightly wider audience. It certainly wasn't an area that I ever thought I'd be working in when I started my career in South Africa back in the heady 80s and 90s down in the goldfields of Klerksdorp and the Wits. But Cameroon is where we are now. So this is just the typical disclaimer. We're an AIM-listed company. So this basically just means please don't take what I say today as investment advice. Seek out a professional who's not a geologist if you're thinking of investing in anything I talk about today. So that's just my back covered. So Cameroon, we believe, and have done for a number of years, we've been in Cameroon now for 6 years, we believe that Cameroon is a massively underexplored country in Western Central Africa. If we look at the geology, the regional geology of the area, to the south, we have the Congo Craton. I'm not sure if you can see my cursor on screen, but the Congo Craton here to the south, the outline of the country of Cameroon here in sort of an orangey yellow, and then the West African Craton across to the west. Obviously, up to the north, we have the Saharan microcratons as well. And if you relocate Cameroon, Africa and Brazil back together, South America and Africa back together, you'll see that the geological, the lithologies of Cameroon carry on through into Brazil, into the Borborema province, where we have evidence of gold mineralization already identified. And again, Borborema province, this crustal structure that runs through Cameroon and Brazil, getting squeezed here by the San Francisco Craton to the south and Brazilian Craton to the north. So what we're looking at here is what we believe to be a globally significant crustal structure, crustal suture. In Cameroon, the main body of this is called the Central Cameroon Shear Zone, and we are actually focusing on some splays off that to the north, the Cholera-Bagno and the Benue Shear Zone. I may refer to them in shorthand, TBSZ, Cholera-Bagno Shear Zone. It's a bit less of a mouthful. We know that the lithology in these areas is predominantly greenstone rocks, greenstone facies. It's metamorphosed metasediments and granitic units, predominantly interpreted to be reworked Hibernian age rocks. And overlying that, much more recent volcanics associated with what they call the Central Cameroonian volcanic line. And this is much more recent, up to sort of Cenozoic age. Now, if we look at Cameroon here in sort of a microcosm, you've got the Central Cameroon Shear Zone, CCSZ, cutting through the center here. Now, these globally continuous shear zones are corridors of shearing. They're not single phases, obviously. And these corridors stretch for, as we've seen down into Brazil, thousands of kilometers in a sort of a northeast-southwest direction, and can be a good couple of 100 kilometers wide. So we are looking, particularly in this presentation, we're looking at Oriol's licenses, which are up here in what we call the Central License Package, or the CLP, and then the splay of the Benue Shear, which comes off the Cholera-Bagno, the TBSZ, up to Bibemi, and then Wapuzi up in the north on the border with Chad. And a long trend from us here, we see the Poyemi deposit in Chad and a couple of other gold discoveries in the immediate area of this shear corridor. Most of the gold in Cameroon has been really targeted down in the rivers in the east of the country, and it's alluvial dredging. There's very little, well, actually, there's no hard rock gold mining currently underway in Cameroon. If you look at the gold production figures for Africa as a continent, you can see straight away there's a huge gap in the center here, and yet we know there's mineralization. We've proven up mineralization in Cameroon. We've got mines operating now, Thor, for example, operating now in Nigeria, right next door. And we know that gold mineralization continues along this critical sort of shear zone through the center here, between the Congo Craton here in the south and the West African Craton, and then the Saharan microcratons up in the north. So we know there's gold in this area. The key point here is, because of various, mainly political factors, there's been very little to no significant exploration in Cameroon. Any gold mining that has been carried out small scale, alluvial workings, artisanal workings, and some pretty minor scale sort of dredging operations in the main rivers in the east. Oriol itself, when we looked at the country, we identified this as an underexplored jurisdiction. But one of the things that we identified was there was a change in the mining code happening. And this really gave us confidence to see that the Cameroonian ministry, Cameroonian government, had recognized that the mining sector could add value to the country, and at the current stage, there are no real revenues coming from it. Royalties and taxes can only be applied if you have formal mining operations, and the informal operations are not allowing the government to capture any of that revenue. So the government took a decision a few years ago to look at what happens in the west, to the west of them, in the more successful mining countries, and they followed their lead essentially, which was to go out and bring in funding from the World Bank, and to use that funding to carry out a countrywide prospectivity analysis, upgrade the mining code, upgrade the licensing structure. So today, if we look at Cameroon as opposed to 10 years ago, BRGM, the French survey, who are real experts in geology in West Africa, BRGM have done a complete country analysis of the entire country, multi-element, remapping, geochemistry, geophysics. The GTK, the Finnish Geological Survey, have come in and helped Cameroon upgrade the mining code. And there's a new mining cadastre, which basically delivers for Cameroon an opportunity for transparent licensing structures. So that's Cameroon. Now, I'll talk a little bit now about Oriole in Cameroon, the work that we've done. And what I hope you'll get from this is that there is still an opportunity globally to get into areas which are totally unexplored and have success. We are, I think it's fair to say, on the AIM market, we are one of a handful, if not the only, junior exploration company which has carried out very, very early stage exploration, grassroots exploration essentially, and not gone down the typical route of going into sort of brownfields areas of known jurisdictions. And we'll be focusing today on the northern areas of Cameroon where Oriole is operating. If we look at the map on the left, with this inset box map to the right, you can see broadly in Cameroon quite a good infrastructure basis, a number of regional and domestic airports, and then international airports, Yaoundé, where our administrative center is based, and Douala down here on the coast, international airports. And then Ngaoundéré, just south of our central license package, is a domestic airport, and Garoua up here in the north, just to the west of our Bibemi and Wapuzi licenses, again, a domestic airport. So we can access these from Yaoundé. With Air Cameroon, we can be up here in about an hour and a half. The red lines on the map are the road network. The green lines are the main power network. And if we zoom in to this inset map on the right-hand side, you can see again the CLP license package, the Bibemi and Wapuzi licenses, and we have a hydropower station at Lardo, just beside Garoua. And you see that the main north-south access route actually runs right through our license package here, from Ngaoundéré north up to Garoua. This road through our license package here is a tar road, a metal road, surface road. And we've been operating in Cameroon since 2018, when we originally did a joint venture earning onto the two licenses up here, Bibemi and Wapuzi. And then in 2019, we applied for this central license package. And this was granted in early 21, and we've had significant success in this area. I will highlight, as we look at this map, if you go onto the mining cadastre for Cameroon, you'll notice that there's a huge density of licenses under application around us. Our license package, when we applied, this was open ground. We carried out a countrywide analysis of where we should be, and this came up as our rank 1 and rank 2 areas. We were very surprised to find it was completely open when we applied. Since then, and since our success in the last couple of years, people have put in license applications all around us, which we see as a positive. Now, if we go to the scale here, what I often try to do when I'm working with our teams out in the field is to try to get them to understand the scalability of deposits and how what you see in the field, how does that translate into something that could potentially be a mineral resource, perhaps something that becomes a mineable reserve, perhaps something that becomes part of a new district. And I've got two images here that I've used with the team to try and communicate this. The image on the left is our Bibemi license, this sort of oblong shape trending northeast southwest, and within that license, two prospect areas, the Bekasi prospect and the Lawa prospect. And within the Bekasi zone, we have here some mineralization, which I'll come on to explain in the slides. And next to that, at the same scale, I've got a footprint of the Chirano mining license in Ghana. Now, this is a similar, we believe to be a similar orogenic system to what we have at Bibemi. And this is really to show to our teams in the field, when you're looking at prospect level mineralization, and please do note the scale bar here, 5 kilometer scale bar, you know, what number of prospects makes a deposit? Are they close enough together to be multi-pit single center operations, as is the case at Chirano, where they've opened up multiple pits along the structural trend and put in a central processing zone. And Chirano is now run to several million ounces. And we hope that the Bibemi project, Bekasi Zone 1 and the Lawa, Bekasi and Lawa, can deliver for us a very similar thing. Now, over on the right-hand side of the image, we again see our CLP, our central license package here, which is currently stands at 9 licenses granted and 1 under application. And this is overlain on a cutout of the Kédougou Kéniéba inlier on the Senegal-Mali border. And what we have in the KK inlier, as they call it, is a number of, it's structurally very similar to what we have in the CLP, splays off a large, crustally significant, globally significant shear system. And here we have multiple multi-million ounce projects and operating mines. And this is really to stress to our investors and to our geologists that what we're looking for in the CLP is significantly different to what we're looking for up at Bekasi. And the reason being, we are looking at very different scales. The scale bar here, if you were based in London, you'd realise that the M25 ring road and Greater London fits well easily within the license package we have out here at the CLP. And we certainly have the potential to pick up multiple deposits in the CLP license package, whereas at Bibemi with Bekasi and Lawa, it's going to be multiple pits for a single project. So that sense of scale is really important. It's something to bear in mind as we go through and look at Cameroon in general. So we'll zoom in on Bibemi. You know, initially, we looked at the orogenic gold systems in here. We came into the project through an earn-in with a local company, BEIG3, which held the licenses of Reservoir Minerals Cameroon. Now, I just, for the sake of transparency, up until the point where we sold Reservoir Minerals, the company, to Nevsun back in 2016, I was the chief operating officer at Reservoir Minerals, and so was involved in the exploration up here in the north of the country. So the Bibemi license, it's an orogenic gold target. We're effectively looking at granitic units to the west, tonalites and granites, and then mafic schists and sediments to the east. The main trend of the structure, as indicated by these dotted lines, is northeast southwest. And these are drill intercepts, drill targets that we've tested. The Bekasi Zone 1, which is where we've developed and delivered a resource. Bekasi Zone 2 in the more mafic units, and then Lower East and Lower West, which are associated with the same structures and we believe give us the opportunity for additional resource. Now, currently we're at, Oriole sits at a 90% ownership of this license with 10% owned by our local JV partner. Now, Bibemi was originally discovered, the mineralization here was originally discovered back in 2012 by the field team of Reservoir Minerals. And it was a very simple story. Quartz veins sticking out of the ground, and those quartz veins, when sampled, indicated quartz tourmaline mineral with associated gold mineralization. Some hand-dug trenching was carried out by Reservoir in the early stages, but for various reasons, the project effectively went into stasis for a number of years. Main reason being when we discovered the gold up here at Bibemi, at the same time we made a discovery in Serbia, which was running 15% copper, 15 grams gold, and that took our investors' eye, and the bulk of our focus went into Serbia. So when we came back as Oriole back in 2018, and we were looking at Cameroon and entry points into Cameroon, the licenses were available, the local partner still held them, and we came in and carried out a very simple boots on the ground progressive exploration program. We came in, we mapped, we did some trenching, this time mechanical trenching with a much more comprehensive sample program along those trenches, and we identified significant mineralization along the Bekasi Zone 1 trend and out here on the Bekasi Zone 2 trend. We carried out about 12,000 meters of trenching and intercepted multi-gram material in the trenches, in addition to bonanza grades in grab samples, up to 135 grams a ton, sort of 3 ounce to 4 ounce material in grab samples. So we took that data forward and we carried out a drill program. We did some prospect level drilling initially, and then we honed in on the Bekasi Zone 1, which was giving us the better results at the time. Being a junior company, we do have to some extent pander to the market and chase the higher grades. And this program delivered for us a significant amount of mineralization at Bekasi Zone 1 and a number of interesting targets in the other areas. Good results, but of a narrow widths in the initial phases. As we developed the drilling phases and expanded the program to a total of close to 7,000 meters of drilling, we had really identified a decent sort of 1.5 kilometers trend through Bekasi Zone 1, and then these additional prospects at Lower, East and West and Bekasi Zone 2. This is targeting shear veins in shears, quartz tourmaline, typically dipping to the west quite steeply, and that was our initial focus of the drilling and led to the orientation of the drill programs that we put in. We had good results early on. Virtually 2/3 of the holes we drilled across the entire prospect delivered gold mineralization. So we were very comfortable that this new target for orogenic gold in Cameroon, this new country for orogenic gold, was living up to its expectations when tested with the Truth machine. This was all diamond drilling, HQ core size, oriented core, and a really good sort of scientific test of the mineralization in this area. And that really led us to the desire to start looking at putting together a resource. We know that these veins that we intercepted mineralization in were typically quite narrow, 2 to sort of 5 or 6 meters, but the grades were good and consistent. And we did have spotty, very high grade zones, indicating, as we later found out from some petrographic work, that there is some gravity separatable visible gold in these systems. Now, the phase 4 drilling, we'd identified.
Sorry, Tim, you have 5 minutes.
Wow, okay. We'd identified that we had a significant cross-cutting relationship of subhorizontal mineralization, which gave us much wider widths, typically down here, nearly 15 meters at nearly 4.5 grams. And this is just a cross-section through the Bibemi Bekasi Zone 1 area, giving you an indication of that. We put together a resource on this. We had an independent group come in and do it, and delivered Cameroon's first ever JORC resource. This is an inferred resource, 305,000 ounces at 2.2. So a good grade and completely open at depth, open along strike, and the other 4 prospect areas obviously still open as well. So a very tight timeline of drilling, 19 months from start to finish to deliver this resource. And that really leads us to a proof of concept for orogenic gold in Cameroon. And that, with that confidence behind us, we move to the central license package, which is again a much bigger scale. As I said, we're talking about 2,500 square kilometers in the eastern block, over 4,000 square kilometers in total. Pan-African age, greenstone host, evidence of mineralization associated with the Cholo-Rabanyo shear zone. Now, we picked this area back in 2019. In 2021, in December, the World Bank sponsored countrywide prospectivity project started to publish some data. And this is an image which was published by that group. It was called PRECASEM. The program was called PRECASEM. And this is the result of BRGM's work across the whole of Cameroon. And you may be able to see my mouse tracing a yellow outline there. And that yellow outline is what BRGM and the World Bank consider to be the most prospective area for gold mineralization in Cameroon. And if you overlay that with our license package, you can see that we've effectively captured the entire area in our licensing. Just to the north of us, northwest and northeast, are forest reserves, and there was no point putting applications in there, so we didn't bother. But effectively, this confirmed that our original prospecting had been successful. And I'll say again, this was open ground when we applied for those licenses in 2019. Nobody had ever licensed this before for gold. We carried out a very simplistic program, very typical boots on the ground geology, identified the main, all of the basin catchments. We did an initial stream sediment sampling program across those basins, ranked the anomalism, followed that up with soils grids on the more interesting from initial glance, more interesting stream sediments. And that delivered for us a number of soil anomalies. We're homing in now on this 2,500 square kilometer area of the eastern CLP. And you can see we've got significant gold anomalism across this whole area. Again, pay attention to the scale bar down here. This is 10 kilometers side to side. So we're looking here at a corridor along the TBSZ and the Benue shear zone, corridor approximately 75 kilometers long, 15 kilometers wide of gold mineralization. We field checked that. We identified typical iron oxide alteration, boxworks after pyrites, and again, grab samples. Our highest gold in soils in this area, 838 ppb. So we know we have significant mineralization. And we focused in on the biggest of those anomalies on the Mbe license, and immediately started finding really good intercepts from rock chips and grab samples along that area. This is one piece of the 12-kilometer long anomalism, focusing in on a cross-cutting semi-perpendicular structure, which blows up in this image on the right. And you can see that the grades here are, in some cases, again, multi-ounce, 130 grams a ton is not unknown, but consistent mineralization along this. And our dear friends, the artisanals, saw the published data. We're a public company, we have to publish the data, and decided to come in and dig a couple of pits and have opened up the ground for us. And we can see here a typical orogenic gold style mineralization, a large quartz tourmaline vein system with mineralization across the vein and bleeding out into the sidewalls. And we see this in several places along the Mbe target. Now, in addition to gold in the CLP, where we've had great success, we did multi-element analysis and we tripped over some lithium anomalism. We've still not quite got to the bottom of this. This is associated with some granitoid intrusives to the southeast of the license package. But there is evidence of lithium anomalism in the multi-element data, and that's to be followed up as we go forward into the next field season. So the central license package, again, this is literally 2 years worth of work from the licenses being granted to the identification of multiple gold targets in this gold corridor, and also some lithium anomalism alongside it. This is just a graphic representation of or rather schematic of this gold corridor. The yellow outlines are areas of, these are polygons reflecting stream sediment basins, which have had positive gold anomalism in them. The solid yellow are areas where soil samples have given us indications of mineralization. And then this gray down in the DOM license here, evidence of lithium in our soil anomalies as well. So we're looking at a corridor here, as I said, 75 kilometers long, 15 kilometers wide, multiple targets. And if you cast your mind back to that image of the KK Inlier in Senegal, our expectation here is that we certainly have the potential for multiple deposits to be found in this area of Cameroon, an area which, let's face it, has been totally underexplored to date. We have additional work coming up in this field season in the CLP. We've done some geophysics, capturing the data ourselves and processing it with a group in Australia. And we're also looking at doing follow-up work at Bibemi and expanding the resource that we've already identified there, and hopefully aiming to get towards the sort of 1 to 1.5 million ounces that we expect to find. So Cameroon, we have effectively come into a country that's been totally underexplored. We have a very strong first mover advantage. And I think we've proven to the industry that there is an opportunity to get into new areas if you're willing to undertake early stage, grassroots, greenfields, generative style exploration. The type of work that the majors used to do, and now it's been left to the juniors, and typically the juniors have struggled to find funding for that type of work. And so they've stepped away from it. Since entering Cameroon in 2018, we've rapidly advanced Cameroon's first ever JORC compliant gold resource, and we're looking to expand that into a potential gold mine. And simultaneously, we've developed this large land package in the CLP, where we believe there's opportunity for both gold and potentially for some lithium as well. And obviously, Oriole, we believe, is well placed to take advantage of that first mover advantage. So I would encourage you to look at Cameroon and areas like that, which for whatever reason have been underexplored in the past, and keep your mind open to whether opportunities like this can come up. This is exactly what happened in Tanzania in the 1990s. I was fortunate enough to be there in the 1990s, and from the government opening the door to external investment in the end of the 80s, early 90s, to the end of the 90s, we went through a massive growth of exploration and ultimately the development of 5 operating gold mines within a decade. Cameroon stands on that same path, and we are very pleased at Oriole to be the leaders in the exploration phase in Cameroon. Thank you very much.
Yeah. Okay. So in Tutugo Resources, we're dedicated to providing long-term shared values for all our stakeholders, including the host communities where the mining takes place, or the exploration, any part of the project life cycle. Okay, cool. As mentioned earlier on, Tutugo Resources focuses on a number of different things, but our main focus area is mineral exploration. But we also have interest in logistics solutions and marketing, which is sort of like our main feed in driving our exploration programs. So what is our vision? At Tutugo Resources, we aim to become a globally competitive mineral exploration and potentially a mining company, while continuously creating long-term shared values for all our stakeholders, including the host communities, and also want to change the face of mining and exploration as we see it, where it's more, it's for the betterment of humanity, and in particular the host communities that we believe should play a strategic role in the entire value chain. So our mission is to create good and discover high quality deposits using the first principle approach, and also including innovative systems. Like now we've taken great advantage of your machine learning and to improve the prospectivity targeting of deposits. Of core values, it's progress, prosperity, and people, triple P. Our philosophy is to engage everyone and be a hands-on approach in whatever we do in our projects. So our focus areas in Tutugo Resources, we look at the minerals of the future and also take into context the current minerals. Our areas that we're targeting, it's lithium, rare earths, nickel, manganese, limestone, iron ore, and also have keen interest in coal, as we believe that it's what anchors our economy. So, and Tutugo Resources, how it was derived and it came about, we have identified an opportunity in terms of the just energy transition as the world seeks to move towards a low carbon economy, which is metal intensive from a high carbon economy. And also the opportunities presented at the local level with the role being played by our government in terms of driving the global exploration capital expenditure from what it currently sits, which is 1% to about 5%. And we see that as an opportunity. And also the opportunity is presented in such a way that in us playing in these areas of minerals is the energy demand, which is projected to be around about 174 gigawatts at about 2050. And this then requires us to intensify our efforts in discovering these commodities to meet the energy demand of the time. So, as mentioned earlier on, we've got a keen interest in different commodities, but our flagship project is the lithium and rare earths project. But for this specific case, I'll mainly focus on the lithium project. But we also have interest in rare earths. We've got a number of prospecting applications in rights in rare earths. And we also have interest in manganese, iron ore, limestone, and nickel. But our flagship project that I'm going to focus on is the lithium project. So why lithium? I think we all appreciate the fact that there's a huge global need for us to meet the supply of lithium. Particularly in looking in the case of South Africa, which have not been heavily exploited, the pegmatites and the granitic material. And we believe that there is potential to find some high quality lithium hosted in the spodumene in South Africa. And this demand, as you can see from the representation of the graph there, in just a short space of amount of time, from about 2020 to about 2025, the demand of lithium would have grown by around about sixfold. And we're looking at 2030, that's around about double that of 2025. And this requires us to intensify our efforts in discovering these new deposits that are hosting lithium. And also looking at home, in the case of South Africa, why we need this commodity, particularly the lithium, is in the fact that we're facing the biggest disaster, load shedding. So we need that energy battery storage systems to store the excess when we don't have load shedding. Yeah. South Africa, as you can see from the graph, we're nowhere anywhere in terms of the production. And this is basically, there could be a number of reasons. As a result, South Africa has not intensified its exploration program for a very long time. It's been dormant for a very long time, and now it needs to be brought back into life. So in our case in Tutugo, looking at the South African geology, which is mainly focusing on the pegmatites and the granitic material. This was just me, with my fellow colleague, Dr. Siandam Gadi, doing some bit of field reconnaissance in the Northern Cape. So what we do in Tutugo, we follow a very simple approach in terms of our target generation, in terms of the lithium deposits. We follow a very simple approach, that of Stena in 2019. where we just first starting phase, which we've completed. It's doing a very detailed literature review, looking at historical information that's available. And that has also assisted us in some cases where we've done some bit of machine learning in terms of target generation, looking at studies that have been done in cases like your Canada and Australia in terms of discovering these target bodies. This is still ongoing work. As some of us may appreciate, machine learning in many cases not been fully accepted as a concept in terms of in geology and in targeting these bodies, but it's slowly getting the traction that is necessary to be accepted as a field that plays a strategic role. And we do some bit of target generation in terms of using your remote sensing systems. We've done that, and we've done some nice targeted field work in terms of reconnaissance, but we in the stages of following up and doing some bit of geophysical work and doing some detailed mapping. The nice thing about in terms of looking at the Northern Cape, you can take the advantage of the huge and extensive work that's been done by the Geological Survey of South Africa. Our prospecting area lies within the Orange River pegmatite belt, around about 100 kilometers east of the well-known Blacksburg project. As some of you may know, the Blacksburg project historically was mined for tantalum, tantalite, feldspars, bismuth, beryllium, beryl, micas, and sorts. It's currently been reworked by a company called Marula Mining, and they've been doing some extensive work in that area. In the beginning of this year, in February, they did their first shipment of high-grade run-of mine of lithium ore. And recently, 2 weeks back, I think also even today, Jason posted something of their latest drilling exploration program at the Blacksburg project. Our project, Prospecting Right area, sits within two domains of the Namakwa Mobile Belt. A certain portion of it sits within the Bushmanland sub-province, and vast of it sits within the Pella domain, sits within the nice pegmatite belt. As we may all know, the Namakwa Natal Mobile Belt is around about 400 kilometers wide, 1,800 kilometers long. It forms of the part of the metamorphic crustal belt that runs from west and southern margin of the Kapval Craton. As mentioned earlier on, it sits within the Bushmanland terrain sub-province and also the Pella domain. The area of interest is mainly made up of Proterozoic, basement granitic, and gneissic rocks. The nice thing is you've seen in the previous slide, we run about 21 to 31 kilometers away from the well-known Vendetta zinc mine in Aggeneys. So yeah. So what then we've done so far, looking at historical data that's available from various sources, we're able to recover some nice high regional airborne magnetic data, as you can see in these prospecting right areas. We also managed to recover some number of historical boreholes within the area of interest. There's nice outcropping bodies within the areas of interest there. And the other thing that we've picked up looking at the historical boreholes in relation with the outcrops and also with regional magnetic data is that you can, we've sort of like found that there's a low magnetic anomaly. And this low magnetic anomaly appears to be associated with pegmatitic bodies, which is similar to that of the Austrian Wolfsberg site. And in certain areas where the pegmatites are a bit shallower, the anomaly tends to sort of like lessen a bit, the magnetic anomaly. In cases where the pegmatite bodies are deep, you'd sometimes find this high magnetic signature that appears to be associated with overlying magnetic rocks. that are situated at the shallower level. As mentioned, we are able to recover 32 historical boreholes within the area of interest. Not all of them are necessarily boreholes, some of them are trenching. The nice thing about them is that we're able to intersect pegmatite bodies that occur between 12 meters and 195 meters at depth, with an average thickness of about 10 meters. That ranges from a minimum thickness of about 1 meter to a maximum of 26 meters. With our partners, they're able to assist in terms of developing a sort of like a preliminary model. You can see the pegmatic bodies intrudes within the metasedimentary country rock. And even in the field, you can be able to, when we're doing some bit of field reconnaissance, you can see the pegmatite bodies appearing at an incline, sort of like an inclined angle into the metasedimentary bodies. And this was basically able to confirm what we had recovered from historical boreholes and also from the field. And also this also confirmed our interpretation that these pegmatite bodies are sort of intruding into the country rock, the metasedimentary, that are associated to that of the that are being mined at Vendetta Zinc International. Interesting enough, even in our boreholes, we're able to find evidence of not complete assays of zinc and copper, lead, and also uranium that was at the time when they were exploring. Okay, cool. And our next step into Tutugo Resources, we aim to do some bit of high resolution ground magnetic just to determine the structural framework, to try and link it up with known geochemical mineralization indicators. And also, where possible, with the pegmatites, we know we've done some preliminary mapping with the pegmatites at shallow depth of 100 meters below surface. We could try to do some electrical resistivity. The nice thing, we've been following the developments in parts like mostly in Namibia, what they've been doing. We've found that it could also be beneficial to do some bit of hyperspectral imaging just to better define some of these mineral indicators. And also thereafter, what we would then inform our geological mapping and do some bit of detailed mineralogical work, petrography, and the sorts. And then where we feel it's necessary to move into the next step, we then do some trenching to bedrock. And that will then inform if we then proceed to do some twinning and infill drill holes. In terms of the sampling, when we do the actual drilling, we aim to ensure, in this case, it's a very, very sensitive thing in the pegmatite bodies of the Northern Cape, to be very, very sensitive to the Nugget effect when you do the actual sampling in the field, and then produce some 3D modeling. So yeah, I hope I didn't go too fast. Thank you.
So yes, today I'll talk to you a bit about Pan-African Resources, and you can see our mantra on this title slide called Mining for Future. And I hope in the next couple of minutes, I'll illustrate on many fronts how Pan-African Resources is using this mantra, not just for our operations in investing and exploring, but also greenfields, grassroots exploration in the Republic of Sudan, and also investing in our communities and the areas around our operations. So as per one of the previous presentations, just a quick disclaimer and forward-looking statement that these are our views and not necessarily views that you should take into account in buying shares. Just a quick overview of my presentation. I'll give you a good introduction of Pan-African Resources. I'm not sure if you're too familiar with the company. Then looking at what we do at our operations, we term it mineral resource definition drilling rather than exploration. And then obviously being the African Exploration Showcase, the majority of the body of the presentation is exploration we're currently doing in the Republic of Sudan. And then I'm glad Maria earlier mentioned ESG, because Pan-African holds that close to our heart. And I'll have one slide just showing and illustrating what we do and how we bring that into mining for a future. So looking at the group overview, Pan African Resources, we're a dual listed company, listed on the Joburg Stock Exchange and also on the AIM market in London. We're a mid-tier gold mining company, producing circa 200,000 ounces of gold a year, mainly from our South African operations, which is the Barberton Mines underground operations, where we've got 3 operations there, as well as a surface tailings retreatment facility. We also have the Evander underground mines, which is ultra deep level Witwatersrand supergroup mine, as well as a major tailings retreatment facility where we treat 1.2 million tons of historic tailings per month through a highly automated modernized plant, cleaning up these footprints of these historical large tailings footprints for community development and agriculture. And then more recently, a quick slide as well on the MTR project, which is the old Mintails. It's 240 million tons of tailings that we purchased all the way from Soweto in the eastern side to Randfontein in the western side, where we're investing a large sum of money as well. And then you can see Sudan, the Republic of Sudan, where we hold circa 1,100 square kilometers of prospective ground. Currently, our surface resources, historical tailings footprint cleanup makes up about 40% of our current production, and the other 60% comes from a high-grade, low-cost underground mines. As we move into 2025 with the addition of the MTR project, that balance will tend more to a 50-50% mix, illustrating that this mining for a future of Pan-African Resources, where we have the high-grade underground mines, plus a cleanup, and investing in our communities, making life better, more healthier for them as well, and returning on our investment to the shareholders. Mineral resource definition, and I would like to take this opportunity, these next couple of slides, to not just tell you what we drill, but why we drill in a certain way. Some of the conundrums we have to deal with on a daily basis. The first one is our Fairview mine, and I think most of us as geologists around the table would have had some studies of a Barberton region, Barberton Greenstone Belt, and specifically the Fairview mine. Here, our flagship ore body is called the Main Reef Contact MRC ore body. We're currently mining it about 1.6 kilometers below surface. It's got a core of about 20 meters strike, 4 meters width, ranging over 100 grams per ton. Now, drilling that from surface or anywhere from a distance is extremely difficult. Drillers tend to deviate, so targeting an ore body of 20 meters wide is not easy. So what we do is our drilling is integrated with our mine plan to ensure that we drill far enough ahead of our mining phases, making sure that we're drilling in the right places to ensure that our mining stays on track and our infrastructure is multifaceted. So we take a cubby that will become later an ore muckpile, and we use that as an exploration cubby at the start, and we can drill up to about 4 years life of mine ahead of us, as you can see in this images depicted above. Some of the recent drilling intersections there, you can see 32 grams per ton intersected in one borehole over a 26 centimeter width, which is not that great, but it illustrates the pervasive fluid flow that we have in this area. Then on the left-hand side of the screen, you see the renowned Sheba mine, probably one of the oldest mines, if not the oldest mines in the world. It's been mining uninterrupted since 1896, is the oldest records. This is the Western Cross ore body, which outcrops on surface. And this specific image is actually above the portal level, which is 6 level. So it's above actual underground mining, below surface. Yet, on our mining right in 2014, we had a nature reserve promulgated over the same area, which makes any drilling from surface quite cumbersome. You don't get environmental approval that easy to drill from surface anymore. Again, it gave us the opportunity to make use of our historic underground mine infrastructure, to use that as exploration cubbies to explore this ore body, which is roughly about 10 meters wide and grades about 3.5 to 7 grams per ton. Then on the right-hand side is Consort Mine. Consort Mine has got its own complexities, and if you listen to some of the academic research that has taken place through Rhodes and other institutions, you will note that structurally it is probably one of the most complex geological settings in South Africa. where the Barberton Greenstone Belt has been pushed and folded in between two granitic or tonalite plutons. So it is extremely complex to try and drill and understand what is happening there. So we take a short-term view in that form that Consort Mine has never had a life of mine greater than 5 years in its 100 years operations. So you can see the image on the right-hand side where we explore for the down dip of known ore bodies, and we continue with the drilling. We don't stop it as soon as we intersect the one structure. And we find up to 2 or 3 additional unknown ore bodies not far in the footwall, carrying grades of over 4 grams per ton and up to 20 grams per ton over these structures. So, you know, these are things that some of the people in the audience and online will have to deal with on a daily basis. You know, drilling is one portion of the thing, but there's a lot of other added pressures from environmental or community related or geological related factors that needs to be taken into cognizance. Our other underground mine, Evander Mines, ultra deep level mine, we mine anything from between 1.5 kilometers to 2.5 kilometers below surface. Drilling this Kimberley Reef, which is a 36 centimeter package from surface, can take you anything between 8 and 12 months from the date of collaring up to reef intersection. Now that's a long time frame for any exploration decisions to be taken. Then also recently, we've just been speaking this morning about the gold price booming. You know, it's currently at 1.1 million rand a kilogram, where historically it's only been, you know, if you look back 5-6 years ago, it was 500,000 rand a kilogram. However, cost has also risen much more than what the gold price has risen. So in an ultra deep mine like Evander, we've recently taken the decision to move away from the standard footwall development and conventional breast stoping to become an on-reef development mine, hybrid with trackless machinery and then conventional breast stoping. So this is great for the financing guys. Make more money. It's a lower cost mining method. It's great for mining engineers as well. You've got trackless machines underground, less people required underground, and for safety as well. However, for the geological fraternity, it makes life a bit difficult because historically you would have had footwall infrastructure to drill your ore body from as you mine towards your stopes. Now all of your infrastructure is on reef. So some of the participants here would recognize lip drilling. It's long inclined borehole drilling. And we've also implemented this drilling at our Evander mines. Basically what it entails is we take advantage of the natural characteristic of a drill hole to deflect in a certain direction to intersect the ore body up to 1.3 kilometers from us. So we take a cubby, which is close to reef intersection or reef elevation. We angle the borehole slightly down and slightly either left or right. And the natural deflection of this borehole will tend to go up and to the right and will intersect the ore body at a certain point. And that can be designed to your specification. So through continuous measurement and monitoring of downhole surveys, we can direct this borehole exactly where we want it to go. And then on a retreat basis, we install directional wedges, which will give us up to 5 intersection points on our reef horizon. So this is specifically for the 8 shaft and the Igole project. The Igole project occurs at the 7 shaft Evander area and has been flooded. This shaft has been placed on care and maintenance back in about 2012, round about there. And it's been flooded to up to about 17 level. We have, in the past 6 months, dewatered the 3 decline system to 19 level, and we're going to continue dewatering that to 19.5 level, from where we can drill out the previously named 2010 pay shoot, which Harmony called the 2010 pay shoot, as they wanted to start extracting ore from that pay shoot in 2010. However, that date has come and gone, so rebranding it to Igole. So this drilling, this lip drilling, will inform a life of mine of 13 years for Evander Mines after being placed in care and maintenance in 2018. And for Igole, a life of mine of 9 years with the ore body still open, down dip and on strike. Then exploration is not just ore bodies underground and aged geology, if I can call it that, you know, talking about Barberton mines, some of the oldest rocks in the world. it's also about tailings resources. And as I said at the beginning of the presentation, we recently, in October 2022, acquired the Mintails TSFs, which is 240 million tons of tailings, as I mentioned, for a price of 50 million rand. That's a purchase or acquisition price of about $1.3 per resource ounce. We've drilled 120 million tons of these tailings to a grid of 25 by 50 meters via auger drilling. Just to put it into your mind, these tailings comes at a grade of 0.3 grams per ton. Being off 0.03 grams per ton is a 10% difference, but that is close to the detection limits of any sort of laboratory out there. So you need to be well aware of the early geology, the young geology of a tailings dam. It's a basic basins or sedimentary analysis in a tailings dam. It is man-made basins, essentially. So all of this, along with high-resolution LiDAR survey, was used to update the three-dimensional models and subjected to a DFS study, definitive feasibility study, which was successful. And it illustrated a life of mine just on the 120 million tons of 13 years, producing around 50,000 ounces, which is 25% of the group's gold over the next 13 years at an all-in sustaining cost of $900 an ounce. Now, it sounds amazing. You know, current gold price, as I mentioned, 1.1 million rand a kilogram, which puts it around $1,850, $1,900 an ounce. However, this is verified through our current tailings operations, such as BTRP and Ilikulu. In this region, close to in between Mogale City and Randfontein, Pan African Resources is in the next couple of months investing 2.5 billion rand to construct a plant capable of treating 800,000 tons of tailings a month through this plant. And then we are busy finalizing a concept study of the additional 120 million tons in the Mintails SA Soweto cluster as well, which will, once we start treating this material, extend the life of mine from 13 years to 21 years. Okay, that was a mouthful. So now let's go to exploration in the Republic of Sudan. First question we get is, why Sudan? So, you know, with a company name like Pan African Resources, obviously you look at a continent like Africa, and then it would be nice if you get a gold deposit or some sort of deposit in something that's Pan-African age, you know, circa 550 to 900 million years. And that's what we found. So in Sudan, early mover, underexplored, Arabian-Nubian Shield, gold has been placed or deposited into this region in the Pan-African orogeny some 600 million years ago. Back in 2021, Sudan was the third largest gold producer in Africa, tied with South Africa at 90 tons of gold produced. It's only got 3 formal mines producing circa 12 tons of that 90 tons. The rest of it comes from artisanal alluvial mining or hard rock vein mining on surface. And I'll illustrate this as well as we go through the following slides. So Pan African had a look at Sudan. We went on a reconnaissance visit back in 2020, and we got to this area called Block 12, which is located the closest point to a working harbor city of Port Sudan. Is about 30 kilometers, sort of on the beaches of the Red Sea. It's a very idyllic place to be in. And we were awarded 5 highly prospective areas covering about 1,100 square kilometers, which straddles the Nakasib Shear Zone. The Nakasib Shear Zone is a major structural discontinuity which separates the Gebit and the higher terrains from each other, with known mineralization in this shear zone. The Ariab Mining Company owns and operates the Hasai mine, which is the largest mine in Sudan, producing about 100,000 ounces a year. And this structure hosts that mine as well. The Nakasib Shear Zone attains a strike length of about 250 kilometers and a maximum thickness of about 50 kilometers as it moves in a northeast-southwest strike direction. Unfortunately, during October 2021, as it happens when precious metals are involved in some form, there was a military coup, and the military basically took over reign of the country. And then later, sometime later, earlier this year, on the 15th of April 2023, a paramilitary group called the Rapid Support Forces launched violent attacks against the currently leading military party or military group. So I'm sure all of you have followed that, what's happened on the news. And Pan-African extracted all of our employees out of the country for time being. In August this year, we revisited the country with security contingent to make sure that we can operate in this area. And we're happy to report that all of our support for, or all of our team is back on the ground as well. What we've seen in this Arabian-Nubian Shield is that there's plenty of styles of mineralizations that was identified. First of all is obviously hydrothermal or orogenic systems such as vein gold, and as well as shear zone hosted deposits. We've got volcanogenic massive sulfide deposits. We've got porphyry type systems, as well as sedimentary and alluvial systems as well. So block 12, and we'll see in some of the images, is characterized by a significant amount of artisanal mining, as I mentioned earlier as well. You can see in the two images on the right below that, you know, when I was in varsity, maybe let me start the sentence like that. When I was in varsity, we went to a field trip in Barberton, and one of my honors student friends told me, you know, the Sahara Desert is 80% outcrop. And we all laughed and we couldn't believe it. But after being there, I can tell you, it's about 80% outcrop. So it's probably one of the easiest terrains to start with early stage exploration, because you can map the geology right on surface. No need for any fancy footwork to do. And that is really what we've done. So in the initial exploration target identification sessions, we sat in South Africa and we used remote sensing to guide us of where to go. We focused on Landsat, operational land imager bands, or levels 1 and 2, as well as ASTER. And, you know, I think we all know about remote sensing and the use of satellite imagery, but I quite find it very interesting that, you know, although these things are available to all of us out there, it's not used to the exact extent that it could be used. For instance, you know, looking at the process data, it's typically used to highlight gosons or hydrothermal alteration in rocks. Also, you can see sheared quartz veins and clay minerals and alterations, as well as geological structures. Processing of this bands or of this data includes color compositing, where you basically take the different levels or bands and place them on an RGB scale. As an example, I've listed two there. If you take bands 7, 5, and 3 as RGB, you produce a false color composite, which is useful for discriminating volcanic rocks, intrusive, and silica-rich rocks. And then you've got another one, 432, which forms a natural color composite. But then you can also do mathematics with these things. You can ration them with each other. For instance, band 4 over band 2 is significant to highlight ferrous type of metals or hydrothermally altered zones. Band 6 over band 7 is quite apparent to enhance hydroxyl-bearing minerals, such as clays. Band 6 over band 5 highlights the presence of ferrous metals again, and band 5 over band 4 tends to be a mask and take away vegetation and water. So we've gone through this study, and the top two slides on the left-hand side is of a specific area in Block 12. And we tried to validate this by doing the same study over known mineralization. So we took the area of mining concession and we did the exact same study over that. And you can see, if I just sort of highlight a specific portion, it's not on. There we go. If I just highlight the center lower portion of the Block 12E Gozan image, you can see that it's a warm color. And then on the image to the right of it, on the alteration image, you get a cool color to that. Looking at the known mine of Hasai mine and Hadal mine, you get a warm color on the Gozan and a cool color on the alteration. So it shows that there's some truth into this remote sensing. And we were quite confident that we'll find something once we go there. We then went to in-field data acquisition, where we've mapped through our geological team there approximately 45,000 hectares of detailed geology on the ground. It's all outcropped. Over 215 rock chip samples, stream samples, and soil samples are collected per month and submitted to the Pan-African owned and operated SA laboratory. So the next question is, why a Pan-African owned SA laboratory? Well, in Sudan, there's no accredited SA laboratory. You've got a ALS sample preparation laboratory, some 600 kilometers from us, that crushes, pulverizes, and splits the samples, and then exports that to either Ireland, Romania, or South Africa. Obviously taking a lot of time to get your results back. So Pan-African opted to have our own laboratory constructed in containers here in South Africa, exported it to Sudan, and we're working to get that accredited and set it up as the first accredited industrial size laboratory in Sudan. This laboratory is capable of doing a fire assay with gravimetric finish, as well as AAS, as well as X-ray fluorescence for multispectral analysis. Stream sediments samples are split into 3 fractions, where we use these fractions to analyze different trace elements or different indicator elements. While the soil scree samples are sieved down to -75 microns, because that's where we find that the gold is located. All of our field mapping and field data collection is done online. There's no paper involved whatsoever. We've got tough tablets installed with the DataMine software suite of Fusion, Quick Logger, and Sample Station. And these interconnect with the Esri ArcGIS Pro, directing our field geologists in real time on the ground. We also employed a multinational task team to ensure that our operations and exploration is done optimally and as efficient as possible. The next step for Sudan is to mobilize the drill rigs. You can see some of the images. I would just like in the next 3 slides to take you through some of the targets that we've got there. First one, which is Kishi, right in the center of that geological map, then Turkish Ridge to the north, and then we've got Satip to the south. Kishi is a porphyry type deposit, complex geology with erosion and alluvial scree on it, with pervasive iron oxide rich material and a bearing parallel structure as well. You can see some of the samples that we've taken there. You can obviously note the quick iron content just visually, as well as in the center lower image, you can see the green nature of the copper. That sample was our discovery sample that came out at 9.7% copper for that specific sample. Rock chip samples or trenches sort of came in at 10 meters at 0.6% copper and also anomalous cobalt and lead. We've got the Turkish Reach as well, which was identified through the remote sensing exercise, which is a northeast-southwest striking siliceous unit dipping towards the northwest between 20 and 45 degrees. It is in close contact with the mafic and intermafic volcanics, and it's got pervasive iron oxide staining as well as silicification. The total strike length discovered there or estimated thus far is 4.2 kilometers. It is important to note that a significant portion of this, although I mentioned that 80% of the Sahara Desert is outcropped, that 20% where it's not outcropped is where the ore bodies occur. And you can see that in the image below with the Polaris standing on this very immature alluvials as well. The discovery sample graded 7.3 grams per ton. Satip is a artisanal mining site, and you can see that in the valleys where in local language it's termed a wadi, the riverbed. You can see how the artisanals have worked this area. Basically, they take excavators and loaders, load it into dry blowers such as in Western Australia, and concentrate the gold from there. Sampling from this concentrate illustrated the gold grades of 29 grams per ton, while in situ gold grades from our soil and rock chip samples showed up to 3.5 grams per ton. Okay, so going to ESG. What do Pan-African do to look after our operations and our community? And I've shown you now, by investing in our operations, by investing in grassroots exploration, now I'm going to show you investing in our communities. We were the first mining company to install and commission a 10 megawatt solar power facility at our Barberton, at our Evander mines. We're currently constructing an 8.75 megawatt solar facility at our Barberton mines, We've also signed a 40 megawatt wheeling agreement with IPP, which obviously relieves a lot of pressure from the local grid in our areas. We've also installed a 3 megaliter per day reverse osmosis system at our Evander mines, where we utilize underground water, which we pump to surface. We clean that up and we use it for our own drinking water needs as well, further alleviating pressure on the infrastructure around our areas. We do develop schools. Tomorrow, we're actually unveiling a school for the Evander region. And we have also established a blueberry farm in our Barberton operations, where 15 hectares of our own land has been converted to a blueberry farm, which is the first farm in South Africa to be in flower and to market. We saw this year that as our trees has matured, that the crop has increased from 120 tons to 220 tons of saleable blueberries. So these are projects that a mining company is doing to look after the community in the sense of farming and renewable energy, as well as water and schooling. Thank you very much.
Thanks, guys. I come on wearing two hats at the moment, MSA Group, as well as Myriad Uranium, which is the sponsor of this project. They are Canadian listed and a few other stock exchanges. And so there are sort of disclaimers, but I'm just going to bore you with that detail. I put it right at the end. So exploration in the Sahara Desert region is, yeah, it can be tough. And I'll get into those details. So it's a arid region, obviously, and it's very rough. But sometimes there's interesting things to look at. Couple of camels in the middle there. Things can go wrong, and they do. So you have breakdowns, but there's always time for a good cup of tea. And if anybody's been in that region before, they would know that it's very sweet green tea. Always take protection with you. 2 years ago, Standard Uranium made a prediction. The uranium market is at a tipping point. The clean energy transition, in addition to supply shortfall, could tip the balance towards an era of rising uranium prices. Turns out that's quite a good prediction. We've seen this kind of pattern before. This was around the boom period of 2007. Real big spike in uranium prices, went as high as $140 per pound at the time, but then came down as quickly as it went up, following the global financial crisis. And then we had a bit of a resurgence, but the Fukushima disaster took care of that. So for a good couple of years since then, we've had depressed uranium prices. What's interesting to note is that to the left of this, from around the period of 1980 up to when the prices started going up, was about 20 years of nothing going on. Very low uranium prices, pretty much flatlined. Now, the last 20 odd years has been quite volatile in the sense that we've had real big spikes and a few movements in between, and then a proper depression again. But Standard Uranium made their prediction around about there where the red circle is. So they might have had the benefit of a little bit of an increase already at that point. However, as of October 2023, we have Cameco reporting spot uranium prices above $74 per pound, which is the highest level it's been again since before Fukushima, in fact. And yeah, there seems to be a magic number of around $65 per pound where a lot of projects become interesting. So in terms of worldwide recoverable conventional uranium resources, these are all the top countries. And you'll notice Australia is dominant in terms of resources potential, but it's important to see what comes next, in that a lot of this has to do with what can be recovered at what price. Niger sits in at about 5% of the total world potential. But if you read up about these things, you'll see that they produce about 40% of the uranium that France requires for its reactors. So it's quite important and strategic in that sense. So in terms of production there, you can see it. Even though Australia has got the biggest potential, it's not the biggest producer. Kazakhstan produces the most, and that's because of its low cost in situ recovery operations. So there you can see in the color coding how this works. The dark blue is recoverable between $80 and $130 per pound potentially, and the light blue above 130. So the price points for your Australian uranium are quite high. Similarly for Niger, it's on the same kind of profile, but as I've said, there's a strategy there as well. Its geographic location to Europe and supplying European reactors is important. So it's not always only about the price. So in the Timosway, just to give you an idea of what kind of resources there are, they're pretty big. The biggest one in Mararan is over 420 million tons, grading at around 600 ppm uranium. By far the biggest in the region, and some of the biggest deposits in the world, for that matter. All in all, these together account for about 1.5 billion pounds of uranium in the ground. There's a couple of other players that have moved in, like Global Atomic, DASA, which I'll talk about, and or I'll at least refer to. And GoviEx is running Maduela. And these are sort of in smaller deposits, but in the case of Global Atomic, you'll see that they have a grade range which is a bit higher than the rest. The only underground mine at Cominac has got the highest grade, of course, which is the only reason why it would be operating underground. So in terms of uranium deposition, uranium occurs in two, sorry, just gonna get rid of something. In two valence states, it's a U4 plus and U6 plus. So weathering of the rocks converts uranium into U6 plus state, in which state it forms uranyl ion UO2, 2 plus. Uranyl compounds tend to be soluble in groundwater, whereas U4 plus compounds are not. So as long as the groundwater remains oxidizing, uranyl ions are stable and uranium can be transported by groundwater. However, when uranyl ions encounter a reducing agent such as organic matter, U4 plus uranium is precipitated, mainly as uraninite and coffinite. And that's what we can see in these types of deposits where you have classic kind of sedimentary hosted roll fronts. You might see a source rock in the area, which provides the uranium into the sediments, transported down the layering, and then it hits the reducing boundary, which sometimes may be affected by structures. And in this particular case, that's exactly what's going on. You'll also see that in the reducing areas, there's the increased content of carbon and sometimes minor amounts of sulfides associated with that, which can become important later. So there are West African basins. These are all intracratonic basins, and the myriad projects are located in the Timosway Basin, which is located in sort of in the middle of the Ilu Medin Basin, which straddles the borders of Nigeria across Niger into Algeria and to the west as well. So it gets involved, but what is interesting or most important to note is this main structure going north-south, which is called the Arlit in Azahua Fault. And what you'll immediately see is all of the biggest deposits are located right along this fault boundary. In terms of the stratigraphy, though, this is the air basement, which is probably the source for most of the uranium. All the sediments transported down into the basin area of the Timosway Basin, and running from sort of Devonian period all the way through to the late Cretaceous. The biggest deposits are located in the Carboniferous sediments down here, and in the upper Triassic to late Carboniferous sediments up here. Chiruzurine 2 is the formation there, and down here is Tarat and others. The lower sediments are also known as the gray series and the red series, and you'll see that in a moment. So if these deposits are fault controlled or structure controlled, what's the tectonic evolution? It starts off with a basement preparation during the start of the Pan-African, which produced the north-south main Arlet fault. There's an axis of a sort of a synclinal, synformal nature going north-south as well along the basin. Then we have a period of reactivation in the late Pan-African, which produced the 140 structures, to 140 to 150, and right lateral faults from an east-west compression phase, and the 70 to 80 structures, strike-slip faults, which, for example, the Tin-Adrar fault. Then we have another reactivation phase in the Upper Cretaceous, producing these North 30 fault trends in a reverse strike-slip trend, and that's from a 140 compressional phase. But all in all, most of the deposits are either located in or related to river channel type fluvial settings. So apologies for the quality of the image. This comes from actual Arriva reporting, and I couldn't do anything about that. It's the way that the image came out. But this shows the scenario quite nicely. And this is actual cross-section across the Imararan deposit, showing major mineralization just before the fault boundary there, and then another deposit on the other side, in the other compartment, on the western side. So the model works. The model shows exactly how these things go, and that sets up the exploration sort of strategy. Here it is in the Arlet pit. You see the gray series at the bottom and the red series at the top. So obviously the color tells it all. And it has to do with the reducing and oxidizing phases of the rocks. On the right, we have what they call a reduced gray coarse-grained sandstone, which is cemented by uraninite. So high-grade stuff. This is just along another trend. So the point, Pierre, I just wanted to make is the major deposits are along the north-south Arlet fault. But what we found in recent times, and other companies have located, is there's mineralization potential along the other trends as well. So Imararan sitting there, the myriad projects are all located around us and along the trends. And then you have the Dasa deposit over there, which is on a completely different trend. And their setting is slightly different. It's sort of a Graben style structure. All the mineralization, very high grade, sitting in the midpoint of this Graben structure. So the model for source, transport, and deposition. The source is the basement rocks with possible bedrock involvement. We have sort of volcanic derived sedimentary host rocks. And then transport of chlorinated brines with the influence of Permian Triassic evaporite levels. Then we have the transfer, which is aquifers, the Arlet fault, and secondary faults. So movement along all of these structures and beddings, which is a result of deformation and abnormal heat flows during the opening of the Atlantic during the Cretaceous period. Then that's also included with convection of highly saline and hot fluids along the Arlet fault. And then finally, deposition is confined and reduced areas along with organic matter and redox boundaries. So all of that is summed up in this model, which shows all the different fault trend directions. The genetic model then is first of all, syn sedimentary uranium deposition during the Carboniferous, followed by early uranium remobilization during the period of around 197 million years ago. Oops, sorry. And then a hydrothermal phase at around 144, with movement along sediments and hitting these boundaries between reduced rock types and oxidized rock types, so the red series and the gray series. Sorry again. And then finally, tectonics during the Cretaceous age, with the reactivation of the Arlet fault, you get deposition of carbonates and other material along what they call the damaged zones of the faults. So what we've seen then is all this mineralization potential along structural boundaries. A lot of exploration has been done in the area. There's a lot of boreholes indicated here. And the red ones, or the red circled ones, are where mineralization was intersected above 100 ppm uranium in the hole, which isn't really that great. We want more than that. So when you look at that, it looks like kind of obvious. Oh, I'm just going to keep drilling around these areas, keep doing what the old timers have done and just kind of drill on a grid everywhere. But it doesn't seem to work all that well. And it was also, this whole process was interrupted by problems in Niger about 10 years or so ago. They had an attack on the Areva mines and in the nearby town of Agadez. So that kind of curtailed exploration activity from their side quite significantly. But as I say, one has to bear in mind that a lot of work has been done, but there's still gaps as well. These holes, lines of holes here are about 5 kilometers apart. So as Tim Lively said earlier, scale is important. You could fit an entire Imararan deposit in that gap there. And as such, on the north-south trends, the closest spacing of drilling is about 800 meters. So we've got regional data. We can try and lean on that. We can try and update these structural interpretations on a reasonable basis, but these are just interpretations. And when you get down to it, it's quite difficult to actually say, where am I exactly going to go and put my borehole now? If it can vary by 500 meters this way or that way, I might miss a target and say, well, I failed in my task. There's lots of interesting information from the ternary diagrams of the radiometrics as well. You can see quite nicely some of the trends in the sediments there and displacements along faults. So there's some good information that comes out of that. But when you can start getting down to deposit level, that's where it becomes more difficult. So we take the project area of Afude, for instance, which is the central project. And again, you can see where the boreholes that have been drilled are located. These north-south ones are 800 meters apart on the north-south direction. The interpretation of faults in the background is exactly that. It's just interpretation files that I got from wherever the source of the information came from. I cannot vouch for it. I don't know exactly where these lines should be. You can see how the Arlet fault just suddenly stops there on the bold line, and the Azusa as well, which is where Dasa is located to the east. So where exactly am I going to put my borehole? Is it going to be over there, or is it going to be over there along the fault? I'm not so sure. So what can we do? Well, we've got interesting information from Areva. They did some seismic profiles across the area. We'll look at profile 5, the east-west, and profile 3. The interpretations of those by Areva at the time shows very clearly where the Arlet fault is located. It has a bit of a listric nature. But interestingly, that's all uplifted material there. None of that area has been drilled. So it's a target area. Similarly, on the north-south line, we've got the Azusa fault coming in and showing a normal fault on that trend. And again, there's a borehole that side and a borehole that side. That whole area of target in the middle hasn't been drilled yet. But we need to narrow it down further. So from the seismics, we're able to say, okay, yes, I can see the fault crosses the profile quite nicely there. I can constrain my fault trend a little bit. On the north-south side as well, the same thing. But seismic surveys are expensive. And what else can we do to kind of narrow down the search a bit? 5 minutes. Okay. So we considered radiometric, sorry, but it's undercover. We also looked at high resolution magnetic. So we decided to do a drone survey of the area to see if we can pick up some of the structural features in more detail. We have, and we also considered electrical methods. We settled on an natural source AMT line on audio magnetic tellurics in the search, which we then replicated along these fault along the profile trends of the seismics to see if we could get sort of a proof of concept. And that was the hatched area is where the drone survey was planned. That's the result of what we could get from the drone survey so far. But as I've said, the Sahara Desert is tough and the drone crashed. So we ended up with a problem. And amongst others, we'll come to that. But from that, I'm able to draw in a little bit more detail of faulting in this area, which could be useful. The AMT lines were performed across those profile lines that I showed. And these can show interesting things as well. Just to zoom in a bit on that area, it definitely picks up the contrast between the one side and the other side. The blue area is showing the down throw of the fault on the Arlott trend. Conductors on this side showing up quite nicely in the sediment trends, and a number of other features that might be interesting. So this does work. It can't tell you very well which way the fault is dipping, so one has to kind of take that into account when planning as well. On the north-south line with the main Azusa fault, again, we can see the disturbance there. The interpretations by the geophysicists show a number of other potential positions of faults that could be investigated and other possibly interesting features. So again, we can strengthen our targeting a little bit, and that's sort of where I'd put my money right now. I'd stick to that area, and I would possibly plan some drilling along these trends here with a lot more accuracy than what we would have had before. The other areas we haven't been able to test yet, and we'll get to that again in a moment, but you know, for instance, that intersection area of the Arlott fault and the fault that comes through from the north, which is where the Maduela deposit is located. They actually, the guys in Canada want to call this Imararan North just because of its proximity to Imararan south of the area. Yeah, and we would look at other areas where there's intersections of faulting potential, you know, if we can narrow down the positions of the faults well enough. But, you know, it's Africa, and we just heard about Sudan. So on the 26th of July, we had another coup in Africa. This guy took over and pretty much put a halt to whatever we were doing. So we've had the crash of the drone, we've had the military coup, and everything's sort of in limbo at the moment. So we haven't been able to go out yet and test what we've learned. And that's the way things go. So, yeah, I think that's it. Sorry, just to mention, they've taken the focus away from Africa to Wyoming. So that's the next thing. I won't tell you about it now. You can go to their website if you want.
Good afternoon, everybody, and thanks for being here. I hope I don't lose my voice. Yeah, so I left industry in 2014 and didn't want to let go of geology. I really enjoyed it too much. So I got some software and started downloading free Landsat 8 images. I then decided I'd actually like to study further and investigate what I could get out of these images. And I started on a PhD. And one of my supervisors was Martin de Wit, who unfortunately passed away. When I got to Martin, I had images covering Southern Africa, and he said, well, why don't you do the whole of Africa? So I had to do the whole of Africa. And yeah, so I carried on going, and my approach to using this data is very different from most people. It's a bit alternative, I guess. I haven't done band ratios. I've just looked at, I've done RGB images over Africa and East and South America to be able to try and trace the structures, the Gondwana structures effectively. Okay, so it's large-scale geology captured by a satellite at 705 kilometers above the Earth's surface. So it's basically looking at the Earth from space, which I think we often sort of forget when we look at satellite imagery. We think it's another air photo, and we can actually use it to draw faults. And yeah, we can map alteration, and we can go higher and higher resolution, and we can try and get more and more detail and all the rest. But as you go for more detail, you get a much bigger data set, and therein lies a bit of a restriction. So you actually are confined generally to relatively small areas. So I took this very big step to just use 3-band RGBs and produce images covering the whole of Africa. So with Landsat 8, which is a vast improvement on the previous Landsat instruments, I took the 2 shortwave infrared bands that I knew were going to give me some mineralogical response, and the 1 near infrared band, and just mapped them, enhanced them, played with them. And I found that the contrast in the results, because you get certain features, for instance, in the red band, you'll get mostly most of the ALOH, FeOH minerals having a drawdown, so they'll come out quite strongly. You've got a contrast with the green band, and then in the blue band, you have the FeOH drawdown. So you're getting a variation between blue, green, and red in your response. So these are just examples of differences in color response, which was not my focus at all. My focus was to follow the structures based on the lithological response, the larger lithological response that came from a mixed SWIR response. And this actually included response from sand-covered areas where material from the subsurface actually mixed in with the sands, and you got a response that actually was meaningful, but at very large scale. So the bottom left, it just shows the clay minerals that are coming off the Angola Craton into Zambia. And then in the middle, we just see those two blue patches, which are very dark minerals. I think it's Karoo. And then on the right, we have is the Griqualand West Basin with the sands on the western side thereof, and a lot of structure coming out, transparency, yellow being the sandy areas with mixture therein. And then, of course, the pink on the right of the Griqualand West Basin are the Malemani Dolomites. Okay, so Southern and Central Africa, we all know the BRGM map, which shows vast sand-covered areas. The Damara Belt is, most of the maps of the Damara Belt show the outcropped areas in detail, and a lot of the work on the Damara Belt has been based on the outcropping geology. And then the Lefillian Arc, similar story to a certain extent, also a fair amount of sand cover to the southwest, and then the Griqualand West Basin, which I'll run over. Okay, so those are the known sort of geological maps of Namibia. On the left is the Damara Belt, mostly in blue, and then the Kakwa Belt. So this is the outcropping Damara Belt. It was formed during the Neoproterozoic, going into the Cambrian, and perhaps even ongoing into the Paleozoic. The closure of the Congo Craton and the Kalahari Craton, and these are effectively sedimentary deposits. This is the Kakwa Belt, and this area here are the late Damara intrusives primarily. And this is an interpretation of those different sedimentological units that were formed when the rift opened and then it closed. And this is what we were left with, these different tectonostratigraphic units. And this is based on stratigraphy and on geophysical data. This is just going back to Central Southern Africa. If you look at what the images are showing, there's a lot here in that sand-covered area that maybe not as much here, but there's certainly quite a bit in here in the Damara Belt that is beyond the outcropping areas. And we can see folds. I mean, these are absolutely undeniably folds, which were not really known. Oh God, sorry. So in this area, we have the Atavi mountain land with Tsumeb mine and Combat and a couple of other base metal deposits, and Nalachab down here. And it's really a sediment hosted, it's a mobile belt that has undergone compression, north-south compression. And then in my view from the imagery, I see that the compression has continued and you have got this folding that developed. this area being a lot less competent than the areas, well, the Kalahari Craton and the Congo Craton to the north. Then I just want to show how I've actually approached trying to, or interpreting these data, because it's very difficult to say, okay, there's a fault or that's offset from that in conventional sort of geological manner. So I started drawing form lines and show you that. Okay, so that's the kind of thing that I started doing. I started defining what I saw in the images. And in this area where the matchless amphibolite belt runs through, and it's the Windhoek-Rehoboth-Gobabis area, it runs dead against that front. And my explanation for that is that it's a fold, and it's a fold closure, because that's what I see in the images. And so I went on. So that is a very sort of broad coarse definition of, or representation of these form lines showing folding in the Damara, and then it has affected the Griqualand West Basin, and in fact it's actually affected everything that is older than the Neoproterozoic, including the Neoproterozoic and the Cambrian. So here we have a very regional Bouguer gravity map. When we combine that with the satellite imagery, there again, you see this folding. Just bearing in mind that this, sorry, I can't really see. Okay, so that fold was actually picked up from reprocessed magnetic data in 2015. But this folding certainly, it was not really recognized for what it was in previous work. So just to verify or to confirm that what I was interpreting to be folding was correct, I got all, got Goscombe's foliation mapping and other foliation mapping and mapped it, and it all, as would be expected, it actually it correlated very well with what's seen in the imagery. And then there's a bit of outcrop here in the Aha Hills, and those foliations also fitted very nicely with that folding. And then there's this gravity map that was acquired by Yorsengrat, and I looked at that and saw that there again, these folds were pretty clear on the gravity map, as was the vergence, the folding that came, or the units that developed from vergence of the Zimbabwe shield. And there again, the Samtex magnetoluric strike vectors. This data was collected in 2007 and worked on by various institutions, and these strike vectors also supported what could be seen in the images, despite the fact that the strike vectors were from well below the surface. So bringing it all together, basically get that folding, as I said, and then just by way of large-scale interpretation, we have the Ovambo Basin there, and it looks like a fold in there, and an antiform, synform, antiform. And these two very large faults, one being the panhandle of the Okavango Delta, and that one. Okay, so going to the Lefillian Arc. Okay, so the Lefillian Arc in the DRC and coming down into Zambia, and a very pronounced circular feature here, which I believe has to be the intersection of two large antiformal features, creating a circular feature. So very dark images, dark response. When I first looked at these data, I thought, oh, I won't worry about Zambia. I don't think I'll be able to do very much with it. But these are the main copper cobalt mines. And then there is the domes area that runs through here, where you've got intermittent domes, doming, basement doming, and uranium, copper, nickel being explored for. Okay, so that's a spider's web of form lines. But what we actually see here is that it looks like there are two different units, whether they are two depositional basins or duplicated depositional basins, whether this is a thrust contact or a synform between two antiforms is not entirely clear to me. But what I believe very strongly about is that because of the orientation of these form lines and these basically fold closures, the way they are orientated, the original deposition of these sediments was in a southwest northeast orientation. So there again, those are the domes, those are the mines, and what we see here that I gathered from a map that I dug up was that the vergence on this side, oh gosh, I lost my triangles. On the left-hand side is to the south, and on the right-hand side is northward. So we have a rotation of the space. So that is what has given rise to these domes. You can see they're all very, very this whole belt is very deformed. Everything's very deformed, and that was probably an antiform at the time before the rotation, and then we got this rotation that changed the orientation of all these outcrops or all these basement highs here. And the okay, so the form lines in yellow are form lines that were mapped quite a while back, and what I just like to point out is that the continuity of the data is what gives this a lot of its meaning. Okay, so there, that is the Damara belt there, as I said, antiform, synform, antiform, and then this kind of folding from continued compression, and the Lufilian arc, in very broad sense, is very likely antiform, synform, antiform, but a very tight synform here or a thrust. And then what's very relevant here is these folds that are trending in this orientation, and then you have the folds that come in from the west. So you've got interference folding in here, and this is where we have a lot of the, well, this is basically the, it's the main mineralized belt in the DRC, but it's intensely folded. And if this, it's very likely that this all resulted from the initial north-south compression, and you had this folding and that folding, and then you had a rotation, and it all sort of clashed together. And those interference folds are very relevant. And there, the domes area, again, a dome, two antiforms coming together and creating a domal structure. And many of these deposits are in domes. And then, yeah, okay, so that is, you probably can't see very much here, but this is a mine called Nkana in the Kafue Dome area. And what you see here is this incredible interference folding. And just to sort of try and make it a little bit more vivid or a little bit clearer, if you didn't see the folding, that's basically what's happening. So you've got this coming this way, that going that way, and this going that way. And your mine sits in the middle. So basically you're creating a low pressure in sediments with fluids in the sediments, and they're migrating into the low pressure area. And that's where your ore focus or concentration is ultimately found. Okay, and then the Griqualand West Basin, that is the Council of Geosciences geological map of South Africa. And just to show that there's a lot of sand cover here. And yeah, and then when we combine the satellite images with the Council of Geosciences map, make the geological map semi-transparent, suddenly start seeing all kinds of funny things. There's a fold here, the fold goes around there, and this comes out here, the bottom of the Durenberg Fault, and effectively that fold in Namibia comes, yeah, it comes around like that. So when you look at the magnetotelluric strike vectors from the Samtex survey, see this is funny, these funny strike vectors. And I don't know that they were ever interpreted. I haven't seen any interpretation thereof, but that holds true with this big fold closure. And that's just like form lines to try and outline some of this folding. So you've basically got, again, you've got effectively east-west folding. That is late. It would be Pan-African, Neoproterozoic. It's so dominant that it's actually affected the craton margin, the Karpfeld craton margin, and all these older rocks one way or another, even if it's just the supercrustals. And then this is a very interesting feature here, a little parasitic fold. So that little parasitic fold that fits in there is dead on the Kalahari manganese field, which is described as being in that orientation. And that's folding is also borne out here, and it goes out there, and it actually continues, but in the more competent units, it's not quite as clear or as easy to see as it is there. Sorry. Okay, so before I sort of got into these after the Damara Belt, I actually then looked at Eastern South America and looked at the geology here and so this belt here, this whole belt was interpreted as the Dom Feliciano belt, which is relatively, well, pre-Damara intrusives or early Pan-African intrusives. And there have been a few different explanations for the relationship between this part of the margin, the Eastern South American margin, and Namibia. And there's a bit of a data gap in here. But effectively, this structure is an antiform with axial planar cleavages. And when it comes together, okay, so this is, this is the free air gravity patterns just to show all the folding that comes out when it's combined with the satellite imagery. You can see here. And okay, when I bring them together, you can see the continuity of these folds, and then a big fold here. So that is the two continent scale geological maps. The one is the BRGM map. The other one is the tectonic map for South America. They're slightly different. This is a 1 to 15,000. That's a 1 to 10,000, but I brought them together at the same scale. And they are superimposed on the satellite imagery. And there again, you can see the continuity of the geology. You see that fold coming down there. See that coming through there, the Damara. And then the Dom Feliciano belt coming down there. And then there has been some work done on sediments right down here in the Dom Feliciano belt and the Harip, and they do fit together. There's also been recently a paper published on Neoproterozoic or Pan-African sediments of, I think they're 570 or 500 and something million years old here. So that definitely was also, there must have been movement there and coming together of those areas north of the Congo Craton. So of course I went and did the form lines and then brought them together and figured that we have synform in here, antiform there, synform, antiform, synform, antiform, and so it goes on. So effectively yeah, okay, sorry. This is all can be interpreted as the late Pan-African Braziliano compression that would have been potentially driven by the closing of the Iapetus Ocean and opening of the Rheic Ocean to create this massive north-south compression and the rotations that occurred towards the end of that compression. And then, so the findings are that megascale coverage from space provides structural context. My idea being that it provides structural context, shows a lot of folding that you could then map, do far more detailed, what you call it, satellite image ratio, band ratio work and superimpose on it, and you would probably get a pretty good target generation map. And megascale coverage from space provides different geological perspective from that on Earth. And the dominance of the Pan-African Braziliano orogeny is very, very clear in these images. And then a lot of my thoughts came from a researcher called Kluting, who talks about lithospheric folding in Morocco, in fact. And then there's the point of the folding creating trap sites as opposed to just straight faulting. So if you think of folding and you think of actual planar cleavages or the faults that are created to accommodate these very big folds, that can give you a very good insight into where your fluids might have migrated and the attitude of, or the orientation of those fractures or those faults in relation to that fold closure. So I've become convinced that folds are the answer, but yeah. So this work basically can bring together a lot of the geochronology that's been done and into large scale geometry. And yeah, so surface structures, brittle folds, generally accommodate megascale lithospheric folds that we cannot see on the ground because we just can't see that far, and we cannot see the curvature of the Earth is also, it's both man's stature and the curvature of the Earth that impedes us from being able to see the folds for what they are.
Thanks, Sue. Any questions for Sue?
Thank you very much. Have you been able to use deep gravity and magnetic worms, to profile the intensity of the gradient of these features?
Okay, no, I haven't been able to work with geophysical data in any detail, but one thing I have always noticed with geophysical data is that it's not as blocky as surface mapped geology. It tends to be very curvy, and that's where, when I first started looking at these data and I was familiar with surface map geology, I thought, how on earth does this come together? But then bringing, the free air gravity together with it, realized that there is something in it.
Another question there.
Yeah, thanks. Just very interesting talk. Very something I haven't seen before. I just wanted to know about the approach you take to actually doing your form lines. What is, if you can just elaborate a little bit more
Yeah,
on that approach and the reasoning behind it.
Yeah. Well, the one thing it's basically I was looking for. I could see a lot of arcuate features in the images, and decided I should actually try and outline them. And when I brought it together with the geology that I had, could actually see that they actually fitted. The geology fell short of those outlines. I do believe that the crust is to a certain extent quite ductile, and the brittle folds, as I said, actually accommodate a lot of that folding. So I really just followed these folds that often were orientated in the same orientation, especially in the mobile belts. You'll get them going in both directions because you're actually dealing with shear zones effectively. And then in the mobile belts, those closures are much smaller than in the cratonic areas where they are much larger and there's less, it's more rigid. So all I can say is that in many instances, there would be contacts, probably in most instances, where the long axis of that fold is really the orientation of the foliation. And then the closure is where it basically meets another surface, I guess. Sorry, that's about the best I can do, but it was very much gut feel about, outlining what I could see, and what it ended up being was a lot of folding.
Yeah, thanks very much.
Okay, good afternoon, everybody. Okay, how's it, everybody? It's an honor to present today at this GSSA conference. So basically, to start off with, I'm working for Ironveld Mining, London-based company, listed on the London Stock Exchange. So the disclaimer, as previously, will prevail here as well. So basically, my journey in a nutshell, I've come full circle. Between 2011 and 2013, I did all the drilling for the Ironveld Mining Company, from bore 1 to bore 160. I logged most of the bores. There's some people in the crowd that have logged with me some of the holes, and did the modeling as well, together with some colleagues over here at MSA. And then 2013, left for another company for 9 years, and then joined Ironveld Mining again back in 2023, January. And so now we've gone into a mining phase. So I'm going to take you back. So this presentation is basically twofold. From 2011 to 2013, all the exploration was done. And then from February 2023 up until now, the mining phase that we're going through. So I'll just give you guys a brief summary of what's happening, and then, yeah, take it from there. Okay, team. So we'll just go through an introduction, the geological setting, exploration techniques that we conducted on site, the stratigraphy of the MML. I will also go through the stratigraphy of the layer 21, which is situated 3 kilometers to the west of the MML, the core logging and sampling that was done, the assay results and some graphs, your mineral resource estimates, layer 21, as mentioned before, some site rehabilitation, and then the current project status, which is from Feb up until now. Okay, so basically, as you can see here, this is basically our project area. We are situated in Limpopo. A lot of the colleagues around you today asked my team, where you guys based? You guys are in the Northern Cape. We're like, no, there is magnetite in the upper zone of the Bushveld complex. And we are based 40 kilometers north of the Mogalakwena mine in the Limpopo province, if you guys all know where that is. Okay, so our mining licenses. Okay, so basically, if you look at this image on the right-hand side, so we've got 3 farms that make up our HW iron mining rights. So that forms part of, that's Krakow, Harriet's Wish, and Aurora. And then we've got 3 farms down here in the south, and that forms part of our Lepon mining rights area. Okay, so we've done exploration in on all these farms, and now we're going to start mining. Our current operations is in the southern part, is in the southern part of Altona, and that's where we're starting to mine. So, yeah, let's go here. So just to give you a brief background, as you all know, Bushveld Igneous Complex, I think a lot of us started our careers on either the western limb or the eastern limb of the Bushveld Complex. And then our project site is situated up over here in the northern limb. Okay, so Ironveld, 40 kilometers north of Mogalakwena or 60 kilometers north of Ivanplatz. Okay. Okay, so just a regional aeromagnetic map with the geophysical interpretation. So as we all know, the MML is found close to the base of the upper zone of the Bushveld Complex. Okay, and then the upper zone in our area is approximately 3 kilometers thick. Okay, there's 21 layers of magnetite that was identified. As I said, exploration was conducted between 2011 to 2013. Okay, 160 exploration bores were drilled, and this amounted to 10,500 meters approximately. Okay, so all this core is at the Sylvania core yard in Mokopane, and all this core, the 3 containers, will be moved across to our mine site in the beginning of the next year for our geos and stuff to do some more structural work on the core. Okay, so just to show you guys here. So this over here is your main magnetite layer. And this area over here, that's where your layer 21 sits. We did 2 or 3 bores where we did drill the layer 21. Obviously, there's another mine in Limpopo that's mining P205. So we're going to look at that for our future exploration. Okay, so just in the field, myself and the team, so these photos were taken between 2011 and 2012. We walked approximately, I think, up to 25 kilometers in the field. Because yes, we had the mag anomalies, but we needed to use the handheld magnetometer to ensure that we drill at the correct places. So I did drill 160 holes. I think I missed 12 holes of magnetite where I drilled in the footwall. I apologize for that, MSA. So yeah, mistakes do happen when you're starting out. But otherwise, we intersected the main magnetite layer and we got what we were looking for. So just to show you guys, for example, if you look at this image bottom left, okay, that's basically your mag anomaly on the left-hand side, which is in nanotesla. Your distance, that's basically, it shows minus 100 to 120. That's basically 220 meters of walking on this cross-section. And we've got our peak of magnetite here. So that shows in this, to the east of this, to the west of this area, I needed to place the drill rig. And obviously, because the dips are between 30 and 40 degrees, you're not exactly sure where you're going to intersect it, but as long as I got that first intersection, I knew then whether to move the rig west or east, depending whether I wanted to go up dip or down dip to intersect a deeper intersection or a shallower intersection. Okay. Okay, so just to show you guys also, there was main magnetite outcrop on some of the farms. That's myself, still in my 20s, no gray hair, unmarried, no kids. So that could be the reason for the no gray hair. So yeah, that's a lot of walking in the field. And I mean, with a team, we found that main magnetite layer. Okay, so just to go through our mining stratigraphy. So looking back, this sort of deposit, you could have probably drilled RC drilling, because I mean, it's white rock, magnetite, black water comes out, white rock again, gabbronorite. But we did all core drilling, and we have all of this core, and our samples were cut in half, and we have all of this core in our core shed. And then just to show you, the hanging wall consists of gabbronorite. Then we go into our main magnetite layer, which is the magnetite, where we have a magnetic footwall, magnetite gabbro, and then we go into gabbronorite again. So guys, this is the contact between your upper zone and your main zone. Obviously, if we had to drill more to the east, we'll go through the main zone and into the critical zone. Okay, there is a mining company that's drilling or that's busy with work to the east of us. Okay, so this was on the one farm, Nonnenworth. Okay, so this is the first area that we drilled. Okay, so as you can see, these graphs basically represent, there's your Fe2O3 percentage top, and the depth in the bore below. So what this represents is that at 23.5 meters down to 26 meters, you're looking at your mag 3, which starts over there and ends over there. So you can see the high Fe2O3 content as well as this bottom portion. This does not happen like this on all the farms, and even on Nonanwith. You have one package of solid magnetite 90% of the time. Okay. And then as you can see, high grade V2O5, 1.3% vanadium, titanium sitting at 17%, and then silica, obviously the inverse of your iron, vanadium, and titanium. So this is a metal producing product, because we're looking at the vanadium and the titanium slag as well at our smelting facility in Rustenburg. Okay. Okay, so just some further, I know there's a lot of geos here, so you guys love the core pics. So as you can see here, this is a magnetite intersected very shallow on 80 in Altona at our mining area. The ball's 8007. So you can basically see there from around 11 meters down to 15 meters, we've got a thick package of magnetite. Okay, so you can see the hanging wall rock is pretty messed up because it's highly weathered in this area and it is a shallow intersection, but your magnetite is competent. So currently on site, we do have a contracted rock engineer, and we are looking at this core and things like that to have a look at our hanging wall stability and all of that as we carry on mining. Okay, then just to show you, so basically CC, that's our northernmost farm, Krakow. HWI 23 is Harriet's Wish, LP is La Pucella, and NW is Nonanwith. So you can see here's the intersection of magnetite at plus minus 93 meters down to 98 meters. So we do have continuity going down dip. The budget was not, I couldn't always drill a 20 meter, a 60 meter, and a 100 meter intersection, but I could drill two holes per line. And I try to get like a 30 meter and an 80 to 90 meter intersection to prove that continuity. Okay. Okay, so just some resource estimates that was done. So basically Altona was the only farm where we could get a measured resource. So there our drill hole spacings was 250 meters, where all the other farms was 500 meters. So we know this is magnetite, it's a bulk commodity. So we know that it is continuous, and we knew that it's there. And then as you can see, density 4.55. And I mean, if you convert your Fe2O3, you're looking at 50 to 51% iron with a conversion rate. Okay, so you have a sitting here with a very good product. And as you can see, your vanadium, titanium, and then obviously P2O5 is very low on your main magnetite layer. But obviously, as you go to the layer 21, it will increase to 8% P2O5. Okay. Okay, but it's fine. It's not spinning. I do have the play button here, but it's not working here. So basically, if you're looking here, this is your Harriet's Wish vein of your magnetite. Here's your Nonanwith vein over here in Nonanwith. Here's your La Pucella, and here's your Altona, your southernmost farm. The reason why we don't have lines in there, no drilling took place there. And over here in Luge, we're busy with we've got a prospecting right. So we're busy with work over there. And once we get the funds, then we will ensure that we start drilling in these areas. And you could increase your resource just in this portion of Luge by over 9 million tons of magnetite. So in this whole area, we're looking at approximately 56 million tons of magnetite. I mean, if we take the 20 to 30% Fe2O3 footwall, and then we're looking at about 80 million tons that we could get out of this project, just on the main magnetite layer, over 28 kilometers of strike. Okay. Okay, so just to give you guys an update of layer 21. So if you look over here, so that is all the main magnetite layer over there. This is your layer 21 over here, plus minus 24 meter thick package. I'll show you here. And what I'm just showing you here is that this ball over here, there's the same footwall, that a north acidic footwall. sitting over here, the North Ossetic footwall sitting over here. So now you know that that is pretty much the same package. And then, okay, so if you're looking at over this image, okay, so basically you've got the PQ layer. Obviously your Fe2O3 has dropped. There's still a nice content of iron. And then if you're looking at, this is very important. So you could see from the previous slide that you have P2O5 between 6 and 8%. Okay, so similar companies in Limpopo province is mining this phosphate. So we're going to have a look at that as well. We're busy preparing a drill plan to maybe look at 100 to 130 drill holes over 24 kilometers of strike in the next year. Okay, so it's going to be an extensive project. I've only got 2 geos, so I'll have to become a geo myself again. Okay, so basically that's your package over there, starting over there, and then that footwall represents this low grade of P2O5 over there. Okay. Okay, again, HWI46, again, one of our layer 21 holes. If you can see over here, again, that's your PQ layer. And again, your P2O5 sits at 6.2%. So this is quite an incredible discovery for Ironveld. And yeah, we'll hope to drill it out and claim a resource soon. Okay, so just the current work that's been done. As you all know, 2 of the geos of our department, MTS department, sitting here as well. So as you can see, we went down the other day and walked about 2 to 3 kilometers, just having a look for potential outcrop in the area. And there was nothing. Similar to how we did it for HWI46, HWI45, we had to use the handheld magnetometer to see where to drill. So I am in discussion with my alma mater, Prof. James Roberts, head of department at Pretoria University. They are looking to get a drone-based magnetometer, and then we will be doing some flying over this area so we don't waste meters and know exactly where to drill. Hopefully this will happen in the beginning of next year or end of this year. And then we'll start our exploration drilling program and then define the resource. Okay. Okay, then just to show you that as geologists, we actually do care as well. So after we drill, I was hoping there's some environmental people in here, so you can see the greenery has come out. So these are our borehole beacons, and you can see we did clean up after ourselves when we left in 2013. Back now on site, everything has grown back. It looks like we weren't there. Obviously, when we start mining, it's a whole different story. Okay, so just a quick, okay, so now that was me 2011 to 2013. This is me now joining Ironveld Mining from 2023 this year. Okay, so this is, okay, so basically this is my 2 geo sitting over there, and we are looking east in the easterly direction. Your magnetite is dipping to the west, which is this way. And when we went to site, because we weren't allowed to blast yet, we went with the whole management team, and they're like, guys, what can we do now to get 6,000 to 8,000 tons of magnetite that we can send to our Rustenburg smelter? So we went down to the pit. Obviously, I wasn't there for a while. And then the geo team said, guys, we've still got magnetite in the sidewalls. So we've got that magnetite. How can we get it out? Because we can't blast now. So what we then did was, so if you look here, you have all of this free dig magnetite that you could potentially get out. So what we did was we got excavators, we got a crusher, we got a screen, and we said, guys, let's start. Let's not idle until our mining rights, until our blasting stuff come through. So now mining right was long time granted. So let's start doing this before we can blast. So what we've done for the past 5 to 6 months, just to show you guys. So this was after some heavy rain, end of Feb in the Mokopane area. So what we did was we took about 1 meter of soil with this magnetite, and we removed that with the excavator. So your stockpiles of broken magnetite and soil over here, just show you here. Okay, there's your excavator. the western sidle of the box cut also contains free dig material, broken magnetite ore. So this portion of our box cut also does contain this. Okay, so before we start blasting and moving to the west down dip, we will ensure that the bulldozer or excavator removes that material. We'll run through the same processes of screening, crushing, etc., and send that to the plant. As you can see here, there's larger magnetite boulders in the area as well. So we can't put through more than 300 mils size of magnetite. So there's larger magnetite boulders that will need to be secondary blasted. So we'll blast that when we're doing our first blast. Okay. So blasting of the magnetite ore down dip will commence December 23 or Jan 2024. Okay. Okay, so what is our geos doing so far? Okay, so basically, Lapon mining just means Lapusela, Nonanworth, Lapusela, and Altona, the three farms combined. This is ball 8025, which was drilled 2012. We intersected magnetite at 26 meters deep. So what we tried to do was we dug this trench over here to try and see if we can get the magnetite that we intersected here in the sidewall in our trench. And we did, obviously, which is highly weathered, because a lot of the questions from our plant was, guys, is the material that you're going to send us now the same as the material that's down dip and within the balls that you said is there? Okay, so it's more of it's metallurgists versus geos, like the stuff that you said is there, is it? Okay, so we said, no problem, we'll show you it's there. So basically, a grab sample was taken from the sidewall. Jan actually took the sample with one of the metallurgists, and to make sure that we weren't biased, they came and checked. And then we took a sample over there. So just to give you an idea, sorry, from down here, from 8025 to this edge of the box cut, you're looking at 380 meters. If we mine down to 50 meters at a dip of 35 degrees, we're looking at 400,000 tons of magnetite. So that is my first goal for next year, is to get that 400,000 tons of magnetite out. Okay. So coming back to the proving statement, just to show you that same trench, 8025 is situated over there. Is Madame Tato Matole sitting over there, but now she's in the trench over here. So basically, just guys, you can basically just see this. This is one of the good things about geology. Not everything is rocket science. If you look at the soil profile here, it's all light brown, whitish, light brown. Boom. There's a color change over here. And then we went for another 40 meters from the side going this way. And again, light brown and brown. So what is in here? Magnetite. What is in the sidewall? Magnetite. What's in there at 26 meters? Magnetite. So you can trace this magnetite down to that hole over there, dipping at 35 degrees. So all of this, before we start blasting, we will rip all of this topsoil away here and then get to a stable gabbronorite, blast our waste, and then blast the magnetite. Okay, simple open pit operation. Okay, so I'm not a metallurgist, but they wanted the magnetite to be 95% magnetic for their testing. So they were a bit worried when they took out smaller material. So I said, guys, no, test the sample that my geologist gave you. And what they found was, this is 8025. You can see they're at 26 meters down to 30 meters. They pretty much got the same magnetic fraction, 99%. They wanted 95% or greater. Almost there. Cool. Okay, so they wanted 95%. We got 99%. Similar silica values, similar iron values. So again, the geologists prove the metallurgists that we know what we're doing. And what we said is there, is there. Okay. Okay, just to show you some screening and sampling. So we're involved in a lot more mining processes now. Just giving advice to the miners. So here's our screen. We're passing through our soil material through our screen. Basically, that's -6 millimeter material, smaller than 6 millimeters. Here's our coarse material, and here's our 6 to 16 millimeter material, which we are sending to the smelter in Rustenburg. Okay, they are tracking that. We've already sent 700 or 800 tons, correct? Thank you. Okay, and then we did, the sampling team came. There's our mine manager, and this is our guy from the plant. They wanted to come do their own sampling, so they came and they did their own sampling. And then what we found out was, if you look here, sorry, I compared these samples. So this is 87, which is the closest bore to that sampling area, okay, to the area that we extracted the ore. So what was, sorry, my fingers are, okay. So as you can see, 87, we got 72% Fe2O3, but now, if you look over here, we only got, okay, that's 46 Fe. So if you convert that to Fe2O3, then you'll get plus minus 66%. So why is it lower? Obviously, because the material hasn't gone through a mag separator. So obviously, you're going to have silica in your material. But I mean, the iron content will be there. When they took out the silica, they got the exact same results as 8007. Okay. So guys, don't always just accept what other people say to you. We told them, get a mag sep, do that, you'll get the results, and they did. Okay. Okay, so here's Jan Mapeka sitting over there, now he's on the screen. There's Ma'am Tole, and there's Tole again. And that is the size that we are sending to the plant in Rustenburg. This is our coarse material that we'll be sending to our DMS plant that's in construction, approximately 500 meters away from our site. So what will happen is we'll blast the ore, input crusher, load it on a belt, send it to the DMS plant, and they'll have their off-takers. So we're basically selling our ore to the DMS plant, which is iPaste. You guys would have read up on that already. Okay. Okay, just to show you, 2 minutes, Cool. Just to show you the first area that we're looking at mining. So there's a 4-meter thick package of magnetite that we're looking at mining. This will be our first area that we're going to blast December or January. We're working on a blasting design to see either whether it's cheaper to do input crushing or if it's cheaper to take our burden spacing, so our blast hole spacing, to narrow that up. But we'll have a look at the explosives and which explosives to use. So we're busy working on that now with the blasting design team. Okay. So geologists don't just look at rocks. We are part of the whole mining cycle. Don't let anyone tell you we just know rocks. Okay, 2 slides left. Okay, so here's our geos. This is me standing on top of a stockpile. This is our free digging area. There's our input outcrop. There's our future mining area. So we're looking at mining down to 120 meters ultimately, and you're looking at the pit being 200 meters wide. So in a perfect world, if there was no one living up north in the other 3 farms, we would have 28-kilometer pit, 200 meters wide, down to 120 meters depth. Okay, a lot of magnetite, vanadium and titanium. Okay, last slide. And this is just a picture of iPace's plant. So this is where our ore will be going from site, 500 meters from us. So our ore leaves here, goes to the site. They'll have their cone crushers and all of that stories. And then they will dispatch from there to the off-takers. Thank you. So as you can see there, if you need any contact details, contact Tato first. She's standing over there. Contact Jan and contact me last. Thanks a lot.
Thanks, Fabian. Any questions for Fabian?
Thank you for the great presentation. I think this is my hometown, so it's a project I feel I am attached to. Yeah, so my question to you only is that how do you plan on free digging the magnetite given the density? Because you need, I think from a mining perspective, you would need to, blast the high density ore. Yeah, that's my question.
Okay, so basically, currently what we did was for that free digging process, we had excavators, crushers, and screens to get out that 6,000 to 7,000 tons that you saw there. What we're planning to do now, we're working with the blast design team from another company, having to look at the different gels. So you get the different nitroglycerine, all of that blasting patterns, whether we use more gas, energy, things like that. So we're busy working on that now, but it won't be a problem to break up the magnetite. I've worked on other projects before where we've broken up the gabbronorite. We've drilled holes through it and we put emulsion. The next day it cracks up. It doesn't work with magnetite. So we're going to look, when we do blast our first blast, we'll be blasting those other boulders, secondary blasting as well, with the same gel that we'll be using there. So we're looking at that now, that process now. I hope that answers your question.
And a follow-up question, Fabian. I think also the infrastructure too. I don't know how far the project is, but in terms of infrastructure, I know there is a lot of struggle with water in the area and electrical infrastructure, which should be in place, I think, before you start the mining. So what plans are in place to, get that up and running before the mining commences?
Okay, I'll start with a water question. Out of that 160 balls that we drilled, I did not intersect any water. So it's very dry. So that is the one problem that we had. We do have a farm up north to the east of us that will supply us with water that other drilling companies around there are using currently. And then in terms of power, I was asked this question during a break. Currently, we are running on generators. Once the DMS plant, we were there last week, there was electrical guys that came there and they were sorting out a box. There's an ESCOM servitude. There's an ESCOM, as you turn off on the N11 to our project, there's an ESCOM base station there. That's probably looking at 3 kilometers from where we're going to mine. And in the future, we'll look at pylons that's going to our mine site. But for now, it's just generators. That's all we can do. And we're looking, I think next year, Feb or March, they're looking at a solar plant. I'm not sure how far that has gone, but that's also an option. Yeah.
Just for context, I thought I'd show this, geology versus geophysics. I know I'm dangerously close to the end of the evening and between you and drinks, along with Bartos. But you've seen a lot of geology and maps and rocks. Geophysics, we try to, tell you about things we can't see. But somewhere in the middle, at least at the top there's beer. So we do overlap somewhat. So today I'm going to examine the impact of the use of radar and a few other geotechnical tools, specifically radar deployed from a borehole, in this case, a 250 megahertz borehole, radar. So deployed from surface, but as well as deployed from underground workings. All our tools are underground, but some are deployed from underground. So this is ahead of mining and specifically to de-risk applications delivering, geotechnical inputs. Platinum. So the case studies I'm going to be showing you focus on the Bushveld complex. Why platinum? This is from Anglo American. There are a lot of uses of platinum, down to like silicones and all sorts, coatings for airbags, all sorts of things, not just rings. The economics are variable. They're looking good. A lot of energy is required to get these things out of the ground. We have most of it, fortunately. I think that's too small for you to see, but still a lot of it's used in automotive and jewelry applications. So the first case study focuses on the development of what's called a hazard index. There were 4 boreholes drilled at the Tumela group of mines in the northwestern Bushveld, Anglo-American operations, and 2 of those boreholes intersected major structures. They intersected dikes, faults, and shears. So the hazard index was used to inform their distillation of all the data that was being captured in those boreholes, something that was simple enough to make use of. It incorporates things like UCS, shear wave slowness, so the speed of sound through the rock, the joint intersection rating, so I'll talk a bit about that, fracture frequency, which are more accustomed to, the spacing, and various hydrogeological information as well. So on this slide, you can see all of those various data sets being displayed. It can be overwhelming to try and interpret all of those in conjunction with each other. On the right-hand side of the slide, sorry, maybe I can just use a pointer. So you can see the televiewer information in this plot. So that's actually a camera inside of the borehole. You can see structures. Those come in optical or acoustic flavors, so you can image through opaque drilling fluid if needs be. There's sonic information, which captures the P and S wave arrivals, so different types of seismic energy that's traveling through the surface of the borehole. That is decomposed into different elastic moduli, so Poisson's ratio, bulk modulus, etc. The televiewers are used to actually pick structures inside of the borehole and those are oriented. So we know the true dip and dip direction of those structures. We can simplify that or summarize that as a fracture frequency, RQD, a UCS from McNally's formula, and then look at actually classifying those things. So it's not just a structure. It doesn't just have a dip and dip direction. We can classify it into different types of lithostratigraphic structures. So we can look at foliations, we can look at bedding, we can look at jointing, etc. And the orientation of those can be grouped into features with similar orientations. Now that's really important because you're not just looking at a single set of structures with a single set of orientations. Geotechnically, if you have different classes of joints at different orientations, depending on how you plan your mine, those can cause geotechnical issues. So we look at classifying those and then creating what is referred to here as a joint intersection rating. So we look at more hazardous or less hazardous combinations of joint orientations or fabric orientations. And then on the right-hand side, the green to orange to red plot gives you this linear combination of all of these parameters and essentially a weighting for hazard. So here is one of the logs. We've now combined it with a radargram on the right-hand side. My next examples will go into a little bit more detail about the radar, but essentially on the left-hand side of the radargram, so over there, is the borehole. On the right-hand side, in this particular geology, you're looking about 40 meters into the rock mass. In this instance, well, in all of these instances, you're looking radially around the borehole. So there is some orientation ambiguity. Fortunately, in this instance, we do have the televiewer information, which is fully oriented. So if we do see reflections from the radargram, and those are from features that are intersected in the borehole, we know what the orientation of that feature is from the televiewer work. So we can now extrapolate away from the borehole using the radar as a guide, but with a fully oriented surface. So if I get this right, this should play. So on the right-hand side, you've got a geological log. That is a dike. So in this area, you've got a dolerite dike, and you can see the contact of that dike in the radargram. The orientation of the borehole relative to the contact of the dike is oblique, which is why you see it's not going perpendicularly away from the borehole, but sort of trending at an angle. You don't see the reflection of the dike contact on this side. There should be one there. It should look like a V or like a K in this case. But on the right-hand side here, you've got these brown units. That's associated with an iron-rich replacement. That replacement has increased the electrical conductivity of the rock mass. The elevated electrical conductivity means that the radar energy, the radio wave, is absorbed and attenuated more rapidly in that formation. So you can see again where I've highlighted it further down in here, you've got these areas where it's just a little bit blank. I don't know if you can, maybe the people at the back would struggle to see the reflectivity, but if you zoom in, actually I can zoom in. Look at that. You can see the reflectivity quite clearly. We've got reflectivity probably at least half the way through that section, so probably 20 meters or more into the rock mass away from the borehole. And a very clear absorption signature here associated with the iron replacement. These features you can see crisscrossing the radargram are all sorts of jointing and contact between the various units that you can see on the right-hand side. Oh, giving it away. You can see again that hazard index, and it's associated with all of the lithostructural features that have been mapped inside of that borehole. So this was then used to do a full assessment of the geotechnical environment where they wanted to continue development of this mining operation. So not only did they do the logging and the radar, they went the next step of taking samples for destructive testing to get static moduli. So here we've got a comparison of the dynamic elastic moduli, which are determined from the elastic waves. So essentially the seismic energy that we're putting from the tool through the skin of the borehole and then back to the tool again. With these destructive tests where they take a sample, take it to a lab and break it. there can be significant differences between the static and dynamic elastic moduli results. And it's attributed to sort of two things, strain amplitude. So you're looking at about a couple of orders of magnitude of range in strain. Those little waves perturbating the rock mass don't move it much versus a laboratory where you're crushing it. But also the samples that have been retrieved from the borehole can be compromised. So you've potentially damaged or changed the integrity of that piece of rock that you've sampled from the borehole. You're now taking it to a lab, breaking it. It might break generally at a lower stress level than you would see from the borehole. So on the plots in the background, you can see the various elastic moduli. And in some instances, there is an underestimation from the laboratory. I can point one out down to the bottom over there. And that's generally the explanation and what it's accepted to be. So moving on to now focusing on borehole radar applications, a little bit closer to mining operations. Bushveld complex is pretty much the best place in the world to be doing radar. The rocks, at least the felspathic rocks, are pretty transparent. It's like looking through clear glass. And you have extremely sharp contacts with extremely different dielectric permittivities. And that generates good reflectivity. It's also very homogeneous, so you don't get a lot of background signal that masks the reflectivity of the features that you're looking to see. So things that we can map are potholes, faults, dikes, etc. Various types of geophysical methods, as you've seen today, are used in exploration prior to mining, some very prior to mining. These are used, as I mentioned earlier, even in underground environments. So we're looking at airborne methods initially, gives you a very good, or satellite methods that are giving you a very good large picture idea of what the geology is doing, but have inherent limitations in terms of loss of resolution with depth. Seismic fills this gap. Seismic retains most of its resolution with depth. It's very different from airborne, other potential field geophysical methods. But still, seismic is a little bit limited with access. So as you can see on the right-hand side, social licenses to operate can be a limitation. Mining rights maybe as well. But geophysics helps with that. So as our depth increases, you know, we can access these things from underground. So here's an example of radar from what's called cover holes, drilled ahead of the mine development, sometimes hundreds of meters. And in this particular instance, how we used radar to detect a methane corridor. Methane in the bushveld. So it is a problem that will grow as the mining gets deeper. Currently, these operations are about 1,300 meters. As we go beyond that, the pressure increases and the associated energy with outbursts of that gas increases. They have resulted in fatalities and other serious injuries. The origin can be organic or inorganic, generally structurally controlled, so moving up through fracture systems, but can be contained in pockets inside the bushveld. And that's associated with mantle-derived gas during the formation of the bushveld. So that's now been formed, but also pressurized since emplacement. Current mitigation strategies that are adopted at a couple of operations include preconditioning. So what they do is they drill a blast hole or an array of blast holes in a panel, but a couple of those holes they'll drill a little bit further, generally double the length. And they will put a small blast into those holes as they're blasting the main face. And that allows some of the stress to be relieved prior to moving that development forward and drilling the next set of blast holes. So I've got little molecules up the top here showing the depths in the borehole where methane was noted to be intersected. So they actually saw the gas bubbling out at the collar. Collar on the left-hand side, drilling through a couple of different lithologies. This is all norite. So the question was, would methane help us to detect the source or potential conduit for these methane seeps? And this is what the radiogram looks like. I think it's pretty unequivocal that the answer is yes. If I attribute that a little bit and separate features that are dipping at different directions, You can see the features dipping this way and over there are stratigraphic units. Those are chromatite seams. And just for scale, this unit there, you can actually see the reflection from the near contact of the chromatite seam and the further contact of the chromatite seam. So that's a 1 meter wide unit. And you can start to differentiate that unit's thickness to give you an idea of the resolution of this data set. These are brittle structures, which seem to be co-located with the intersections of methane in the borehole. And then you can see there's a couple of these hyperbolic sort of features, these curved features here. And those are manifestations, those are artifacts of compact reflective sources. So if you do have a gas pocket, for example, you would expect that sort of dispersion effect to be associated with compact sources. And again. So this is what the geology in the Eastern Bushveld looks like. I was out there a couple of months back having a look at this. It was about 20 years ago that I went there as a student. This is the Dwarsrivier outcrop. It's a World Heritage Site. I encourage all of you to go there. But to look in detail at these chromatite seams, they are quite complex. It's not just a meter of chromatite and then nothing. So I want you to focus on those guys. So those are acute structures, jointing, that are cutting straight through this felsic and chromatite sequence. If we look at how we can process the data, we can start to remove certain features from the data based on its orientation. So if you do have features that are subparallel to the borehole or features that are at an angle to the borehole, we can start to separate those out for interpretation purposes, just to clean up the data set a bit. So you can see in this instance, we've kept the features dipping to the bottom left of the screen. Now to focus on a little bit of the ambiguity. Some of you may have used ground penetrating radar, which is a unidirectional antenna essentially. So you're looking only in one orientation. Borehole radar doesn't have that luxury. The sensors are omnidirectional. So you have a wave field that's moving from the borehole out away from the borehole. So you get this sort of cylinder of investigation. If you do get a reflection back, you don't know from which orientation that reflection came from without some a priori information. Fortunately, in the Bushveld, we have a pretty good understanding of what the lithostructural environment is, so we can kind of predict what the reflectivity should be and then test it with radar. So if you have that reflection in your radargram, it actually forms a cone, or if it's parallel to the borehole, you would get a cylinder. So you must rotate this thing around. You actually get a sort of an hourglass because it could be up that side or down this side. So now what we've done is we've taken that radargram and we've projected it above the borehole in this instance and below the borehole. So you've mirrored it top and bottom. These are FK filtered. So what we've done is allowed that feature to continue straight across the borehole instead of forming a V shape. So now we start to overlay some geology. This borehole happened to be in the footwall. So we're imaging the chromatite seams into the hanging wall and a bunch of brittle structures that seem to be, in some instances, disrupting the chromatite seams, certainly disrupting the reflectivity from the chromatite seams. A little bit of ambiguity because it might be that, it might be that. So there's two different scenarios here. You don't know if it's an upward trending feature or a downward trending feature. If we look at how this data would be incorporated into 3D for interpretation, there we've got the sections plotted up from above the borehole and below the borehole, but we can also plot it to the right of the borehole or any orientation basically around the borehole. So we need some constraints. We need to know, okay, the geology is flat lying, it's generally dipping in this direction. Without a priori information or information from a televiewer, we would need to rely on some sort of geological understanding to be able to interpret these features. So if we look at those surfaces now, we might say we expect flat-lying geology. So we're going to interpret that blue horizon like this. And it's above the borehole. If we interpret that orange reflector in the horizontal plane, you might get a steeply dipping feature that's trending that way, northwest. If we interpret it in the vertical plane, it would be a less steeply dipping feature, dipping to the north. So a little bit different. We would integrate things like Televiewer. One can also use multiple boreholes to sort of triangulate and get a sense of where these things are. So we thought we would bring in some geological truth to this. So it's not just geophysics. This is the first intersection at just over 100 meters. And you can see zoomed in on the bottom here, you've got quite a lot of fracturing. I note just in the top, it seems like there's a bit of iron-related alteration in these norites as well. And at 162 meters or so, you also have these small disking type features. So that's only a few centimeters. I think that's about 4 centimeters. And another zone there of 10 to 15 centimeters. So that's giving an idea of how substantial these structures are in the ground. In terms of improving the success rates, we've got multiple things that we need to cater for. So there's multiples. So you don't just get a reflection of a feature and then back to the tool. You might get reflections from geological features that pass the tool, but then get reflected off another feature and come back again. So you have essentially echoes of echoes. Those things start to superimpose each other, those anomalies. And you can have those superpositions in time as well as that associated angular relationship. So we can do some modeling. We can take a geological surface. We can say, if we had to drill a borehole here, what would the radargram look like? And you get something like this as a synthetic model. We can then take the radar once you drilled the hole and acquire real data and start to see whether there's a correlation in what we expected to see and what we actually did see. That is really useful for interpretation purposes as well. And interpretations of those features then might be fed back into your geological model to iterate it and improve the level of detail. Commercial impact. So drilling boreholes in 2007 cost 137,000 Rand for 3 boreholes, cheap at the price. And radar came in at 86,000, but the data density is quite immense, juxtaposed with a single pierce point. Current drilling costs, probably 300 Rand to about 1,000 Rand a meter. And then if we come back here, we've got those features, but we also have this feature. So that's a subhorizontal chromatite stringer. They can be millimeters to centimeters wide. They are geotechnical issues. They're related to fall of ground. You may be more used to drill rigs that look like this, but there's some drill rigs that look like these as well. And fall of ground is a major issue. We can use radar in blast holes ahead of the mine development and inspecting a hanging wall, which is not yet hanging. You haven't yet blasted it. You haven't excavated. It's safe to be at that space because your hanging wall is supported with roof bolts and with meshes. So essentially, we're looking at putting radar into these blast holes like that and imaging reflections off of these chromatite stringers that are proximal to the mine developments overhead. So you get these reflections, you build up an array of little short radargrams. Each one of these holes is like 3 meters, so not much to work with, but you have lots of them and you can move the transmitter and receiver pairs around to get better coverage. You can start to track features there. So you can make a hypothesis that if the feature is where you think it is, it should do different things. It should trend different ways when you move the transmitter and receiver around. So you can test these hypotheses. And then blast after blast after blast on a longer drive, you can start to build up a longer radargram if you stitch all of these together. And ideally, we would end up with a product that looks like that at the bottom, a long multi-tracked interpretation of what this chromatite seam looks like in the hanging wall to de-risk the mining. What's happening here? Next. There you go. So that's it. We looked at the hazard index. We looked at geotech parameters. We looked at the methane detection and fall of ground avoidance.
Good afternoon, everybody. Hopefully this will get us to the beers all safe and in good condition. But I will be checking for eyes closing and heads nodding off, but I'll also be checking for big open eyes because that either means you're falling asleep or you're waiting for your first beer. So I'm going to be checking for that. So I was invited to give a talk. I asked about what, and they said the Northern Cape, and I was like, okay, well, let's see what happens. Now, my big passion is the iron and manganese, which I'll mostly focus on in this talk, but I will mention some of the other things as well. And being an academic and a lecturer, I'm basically sort of going to tell a story of how we understand what's happening in the Northern Cape. And then hopefully the really industrious exploring and mining geologists will find some inspiration as to where to look and where they think there's still some interesting deposits to be found or some money to be made from existing deposits. So let's kick off. So the Northern Cape province, largest province by area, but I think the lowest by population, mostly a semi-arid climate, and the underlying geology in this area is absolutely fantastic, very interesting. So you've got the northern, the western part of the Kaapval Craton going in there into the Northern Cape with Neo-Archean to Proterozoic successions, mostly the Ventersdorp, Transvaal, and case supergroups. And then there's also a lot of interesting accreted terrains to the west, which contain some pretty important economic deposits over there. And then, of course, just to make life interesting and more difficult for people doing research and exploration in the area, a lot of stuff has been covered by younger Karoo supergroup rocks, as well as a lot of sand, it being a semi-arid area and environment. So some highlights of the commodities we get there is the Northern Cape is mostly known for iron and manganese mining, especially manganese. There's quite some significant base metal deposits, mostly copper, lead, and zinc. Actually, the oldest mine in South Africa sits up close to Springbok. I think even in old Simon van der Stel's days, they trekked up there with wagons to dig some copper out of the ground there. When you go visit the area, you're like, well, that's not hard to do because you can still see green and blue colored outcrops up there up to this day. And then also diamonds, but I'm not going to talk about the diamonds. There are kimberlites. There's the stuff along the Orange River and the Vaal River, and also there along the coast close to Kleinseer. But when I was an honor student, we did a field trip to Cullinan Mine. And by the third time they x-rayed me, I decided I will never work with diamonds. So I moved on with my life. So no offense to the people working in diamonds. Clearly, you love punishment more than me. And you also find the mantle and river sediment more interesting than I do. So, and I'll be honest, I've gone to some mantle and diamond talks that are pretty exceptional, even though I probably didn't understand half of it. So just to say where everything sits, now manganese is a hot one. It's South Africa is a very big country, top producer of manganese, all of it coming out of the Northern Cape. It's an absolutely critical commodity because if you don't have manganese, you can't make steel. That's the main use. People have also been punting that it can be used in lithium batteries, but there your limiting factor is the lithium, not the manganese. So at the moment, I think only 2% of manganese is used in that application. And there are two main deposit types it occurs in, although there are smaller, more sort of oolitic deposits, as well as some more recent hot spring water-related deposits in the Cape Supergroup. The two main ones are the Banded Iron Formation-hosted ones in the Hotazel Formation of the Kalahari Manganese Field, and then the Postmasburg Manganese Field, which is the karst-hosted manganese deposits occurring in the carbonates of the Campbell Rand subgroup. So to first look, where do we get the Banded Iron Formation hosted ones? They're a very tiny little block there in South Africa and in the Northern Cape. And there you get the Kalahari Manganese Field, mostly 3 deposits there, the main Kalahari deposit and 2 smaller deposits to the north. But just that deposit contains, some people estimate, up to 90, but more conservative estimates puts it at 77% of the world's known land-based manganese resources. So small square, big influence. And then this is the Marumani Dome, where you get Sishen to the north of it, Beeshoek to the south, and right in the middle you get all those black pock marks on geological maps, and those are these sinkhole karst-related Postmasburg manganese field deposits. Then what about iron in the Northern Cape? A lot of it around. I think with iron, of course, you're competing with other markets where it might be cheaper, or markets that are much closer to China, although traditionally some very high-grade iron ores have come out of the area. Here it mostly occurs in these banded iron formation hosted deposits with some reworked iron ore often sitting on top of the banded iron formations as well. And that sits in that area there all over the Northern Cape. The big ones sit in the Marumani Dome, but there's also smaller iron deposits away from the Marumani Dome in that region. So for example, yeah, I highlight there to the north there, you get Sishen and Kumani, south of this anticline, eroded out anticline. And to the south there, you see Beeshoek. And yeah, I still have it as Welgevonden, but it's now known as Kolomela. What about base metals in the Northern Cape? A lot of interesting deposits there. There's some debate still around the research in these deposits and how they exactly formed. But generally speaking, you get all these accreted terrains, the Kayan, Bushmanland, Ariagap, or as some people say, Area Chap, and the Kakamas terrains. And most of the well-known deposits here is in the Aggeneys-Gamsberg. There's lead zinc, which is in the Bushmanland terrain, and then you get a whole bunch of what people think are volcanogenic massive sulfide deposits in the Ariagap terrain, for example, the old Copperton deposit close to Prieska. And just to show you where these sits further north, there's to the northwest is Aggeneys-Gamsberg, and then further to the east, you get all these VMS deposits in the Ariagap terrain. Now, I'm going to tell a story, and then within the story, I'm going to say, what are the important events as we see it in geology, or what we understand at the moment, that led to significant ore deposition? I think it's always important to understand when and how things formed, because it can in the future inform your exploration targets or exploration activities. So we're going to skip the Ventersdorp because it's just a whole bunch of lava, and it makes the drive to Kuruman very boring because everything's just flat. Although when you do see it in outcrop in places like Klippriviesberg and so on, it is quite I'm not trying to underplay it. It is a beautiful lava unit for teaching purposes, maybe not so much for economic purposes. So we start with the Transvaal and the deposition of the Campbell Rand carbonates above the Schmitz-Drift subgroup. And this one's very important because that hosts all these karst-related manganese deposits of the Postmasburg manganese field. Then we get deposition of the Asbesievel subgroup, which is the Kuruman and Griquatown iron formations. These are important because they host Sishen, Beeshoek, Kumani, Kolomela, all hosted within the succession. Then we get the Kuga subgroup on top of the Griquatown iron formation, also important because that also hosts quite a few iron deposits, like, for example, at Rooinekke. And there's also some new deposits towards the southwest of the Marumani Dome being explored. And some people are floating the idea that those might be hosted in Kugas rather than the Asbesievels. And there's also some manganese deposition in there as well. And then we get the Maganyeni dimictite, academically interesting, probably a snowball earth-related dimictite. Then we get the Voelwater subgroup. Now, the Ongeluk basalts are not included in that. I just got the timing on my animations wrong. But now we get the Hotazel formation followed by the Mooidraai. And that's where the Transvaal supergroup terminates in the Northern Cape. Now, the reason I talk about this deposition is specifically the Hotazel formation. And why is that interesting? Because the Hotazel formation, as I said, probably more than 75% of the world's land-based manganese deposits. And the vast bulk of that sits in these manganese formations that are still basically primary to early diagenetic chemical sedimentary manganese rocks. Now, for iron ore, you usually need a major epigenetic event to upgrade the grade of these iron ores. In the Hotazel, the vast bulk is mined from this lower manganese bed, which is a pristine chemical sedimentary rock. So understanding what those chemical sedimentary processes were doing is in some way important. And that is one of the few examples, especially from iron and manganese point of view, where nice primary chemical sedimentary rock is mined as it is. And that is where it sits. And super interesting deposit because there's 3 manganese beds in it. It literally has 3 chemical sedimentary cycles going iron, manganese, back and forth. We're still doing a lot of research on it to fully understand exactly how that formed. But also important here is the lower bed is traditionally the one that people have been mining. But when you go to the north of the main Kalahari deposit, the upper manganese bed actually starts thickening significantly. So that could in future also be a significant source for or resource for manganese going forward. And there's just a picture. This is from the southern Kalahari manganese field to show the drill core. And it's very nice and easy to see in drill core where you go from banded iron formations into these black stained rocks back into banded iron formations. Also, the people at these core yards, they're super polite for us academics, especially in the Kalahari manganese field, because where the core is halved, that's where the manganese beds sit. So in case you miss it, they really point it out for you. And here's just a little cross section. And this is also important to show that the Kalahari manganese field, these chemical sedimentary rocks, they're dipping towards the west of the Kalahari manganese field. And if you look at current mining in the area, a lot of it, and now I'm going to draw a line. There's a very small sort of subsurface semi-geological map there at the top right. Now I'm going to draw a line and show you the satellite image. So if you look at the location of most of the current mines there, which most of them, with the exception of Gloria and Nshwaning, maybe one or two others, they're all open pit mines. And they basically, it's literally a case of they're only scratching the surface here. The vast bulk of the reserve or the resource is sitting dipping down towards the west. So if people are willing to start sinking shafts, more shafts to the west in this area, there's a lot of manganese still to be mined. So most of it has been done open pit. We've known about this deposit since it was discovered in 1907, first mined in the late 1930s by Guido Sacco, and it's only really ramped up to make South Africa the #1 manganese producer probably in the last decade. So it's traditionally been quite an underutilized deposit. So with the current activities here, it'll be mined out in 20 years, assuming you stick to current activities. So some mines like Gloria and Nshwaning has gone underground. Now, if they're now willing to start going underground, some people estimate this will, at current usage rates, provide the whole earth with manganese for the next 5,000 years. That's the size of this deposit. Some people think it's the largest single ore deposit in the world, continuous. So it's quite world class. And that's all mostly primary chemical sedimentary rock, which for me as a person that love these rocks, I find that quite fascinating. Also to note, there are 2 outlier deposits to the north. I often get phone calls from random people saying, so where's the rest of it? Where does it sit? And so on and so forth. So what is known is there's directly to the north, the Avontuur deposit. There's not really mining there yet, but I think Orion Minerals is quite a bit of work that they're doing up there. I think Aquila Resources was in there. Aquila, thanks. So they've drilled, there's quite a few old cement core holes there as well, and it looks like it has quite a bit of potential. And then further north, there's the Leinster deposit that was drilled by Anglo American, but the drill core there, I've seen it's more dolerite than actual manganese. So either it needs more drilling or it might not be as economically viable as the Avontuur deposit. But just the main Kalahari deposit that I just mentioned is, will probably supply a couple of 1,000 years of manganese, as long as you're willing to sink a shaft. So now we move on. That's the Transvaal supergroup and the Kalahari manganese field. And there it's just a case of being willing to mine further and explore further down dip. And maybe someone will find another outlier somewhere in the future. Now, between 2.4 and 2.1 billion years ago, the Transvaal supergroup in the Griqualand West region underwent some sort of deformation. There was maybe some orogenic event. It's very hard, not much is preserved, but what we do know is that these beds were folded and tilted, basically. And then something very important happened from an economic geology point of view, and that's between about 2.1 to 2 billion years ago, there was a massive erosional unconformity that formed. It's called the Pre-Gamagara unconformity in the Marumani Dome area up in the hot Hotazel or in the Kalahari manganese field, they call it the Mapedi unconformity. So that basically cut down throughout the pre-existing Transvaal strata. And why is this so important? We think this was a major supergene enrichment horizon. Now, there is some debate as to how some of these ores formed epigenetically. Some people say they're all supergene. Other people say they're all hypergene. It's probably a combination of both. But wherever this unconformity cuts through a dolerite dike and you do the research on it, it looks almost identical to a modern lateritic weathering profile. And when you've got iron formation in a lateritic weathering profile, you're forming high-grade iron ore. And that is even still happening today in places like Brazil. So where it intersects the carbonates of the Campbell Rand, basically it takes hundreds of meters of what used to be dolostone limestone, dissolves that out in a karst landscape, but the little bits of manganese that were in the carbonates to begin with are residually enriching and being deposited in the bottom of these cave deposits. And that is how you get the Postmasburg manganese field. And you can see here, there's a cross-section showing the Pre-Gamagara unconformity at the bottom, a cross-section through the Marumani Dome, at the top, a more regional cross-section. And where it cuts through the carbonates here in the middle of this anticline, that is where all of these deposits in the Postmasburg, say that 3 times fast, manganese field sits. And wherever it intersects the banded iron formation, you see high-grade iron ore. Now, the famous ones are obviously these ones here sitting on the flanks of the Marumani Dome, which is Sishen and Kumani to the north, Beeshoek and Kolomela to the south. Absolute world-class iron ore deposits. So, for example, here's a picture one of my master's students took at Kolomela, and you can beautifully see the high-grade iron ore sitting above the oxidized BIF, sitting directly below this unconformity. And if you also look at Sishen, for example, that's sort of a 3D reconstruction of one of the pits there, and you can almost see how the ore is sitting down into what possibly was a big sinkhole, which it sank down. So for these super large deposits, we think it was a combination of the supergene enrichment, but also these blocks of iron ore dropping down into sinkholes that would probably do 2 things. Firstly, when rocks sit lower, they get less eroded, which improves the preservation potential, but also you're placing it in an environment where the circulating fluids can become very alkaline, and alkaline fluids are very good at dissolving silica, and silica is the one thing you want to go away. Because if the silica goes away, what's left is almost pure iron oxide. And some of these ores, especially at Sishen, run at 99% plus hematite. It's almost pure iron oxide. So very nice deposits there. But also, where this unconformity cuts through the iron formations in the Kuga subgroup, and even the iron formations in the Hotazel formation in the Kalahari manganese field, there you would see the same effect. It's just not as big as you see at Sishen or Kolomela, maybe because there wasn't this castification effect. But this is a picture from Rooinekke, a mine about halfway between Griqua Town and Groblershoop, and it has been mined before, and there you see almost, if you didn't understand the context, it would look almost identical to Sishen or Beeshoek, where you see this Pre-Gamagara unconformity, under it high-grade BIF-hosted ore, over it reworked high-grade conglomerate ore and some shale. And even in the Hotazel formation, and last week we had a very nice workshop in the Northern Cape where South 32 was kind enough to unpack different cores from the Hotazel formation. And in the one core, you can see a couple of meters of high-grade iron ore sitting directly beneath this unconformity. And when they opened the smelters in Pretoria, decades, long before they even opened Sishen, they were essentially putting ore out of the Timeball Hill formation, oolitic ironstone, through that processing plant. But when they were running short, there was no Sishen, there was no Beeshoek. There was actually this high-grade ore from the Northern Cape, from the Hotazel formation, was sent there as a byproduct from the manganese mining. So it's actually this ore was the first iron ore out of the Northern Cape to be put through the smelters in Pretoria. Just a little bit of history there. So that is very important, this Pre-Gamagara unconformity within the broader context of the Northern Cape's big ore deposits. Now, in geology and geochemistry, they talk about the boring billion, which is from about 2 to 1 billion years ago. Now, in the Northern Cape, that is essentially just the rest of the deposition of the K supergroup. And it's not really known to host big ore deposits of any kind. So you can almost say from an economic geology point of view, the Northern Cape had its own little boring billion happening. And also the other problem you have is there was a fundamental change in Earth systems. So you no longer deposit iron-rich rocks. Banded iron formations don't occur in this time period. And there's also no real manganese enrichments either. But now you get the Kais-Namakwa orogeny that happened from about 1.2 to 1 billion years ago. They originally put the Kais orogeny as older, but a lot of now fieldwork think that the Kais and the Namakwa are very closely spaced together. And in this time, firstly, it accreted all these terrains that got the base metal deposits in them. And there's a chance that a lot of these deposits had already formed somewhere else on Earth, and the plate tectonics accreted them to the west of that Kaapval Craton, just adding additional deposits to a part of continent that's already quite mineral rich. So there it does seem that those accreted terrains, that ore formation is not really related to that accretion, and there's a good chance some of those ZX and VMS deposits had already formed previously before these little strips of land was accreted onto the Craton. So for a big example of that, for example, the one deposit that has not been mined yet, just as an example, is Big Syncline. It forms part of the Aggeneys-Gamsberg ore district. At the moment, Vedanta is in that area, and there has been some drilling campaigns through there. So just an example of one of these base metal deposits. We know it sits there, but it hasn't been mined yet. And it's until probably they strip mine it at some point. It's quite a nice place to take students. You see beautiful features, you know, so for example, like a goss, an oxidized cap, and if you pick up some of these rocks, you can beautifully see the skeletal remains of where these sulfides used to be. So it's a wonderful place to take students to look at what people would have looked like in the early days of exploring for these base metals. But that's not the only important thing of this Kais-Namakwa orogeny. It also caused quite a lot of ore upgrade in the area. The big one we know of is the Wessels event in the Kalahari manganese field, where towards the north of the main Kalahari deposit, a lot of fluids were pushed up through normal faults and essentially took your low-grade Mamatwan ore sitting at 38% manganese and locally upgraded that to 60% manganese. It's an ore that also has a slightly higher iron content, so it usually gets used it has other applications in steel making than the low-grade Mamatwan ore, and it's also way less than the Mamatwan, but it is still an interesting event that led to, at least locally, these very high-grade occurrences of manganese ore. It also duplicated a lot of strata, mostly through what we call the Black Ridge Thrust Fault. Originally, they mapped Transvaal strata at Sishen. They mapped it in as younger strata, part of the overlying Gamagara. And later someone went and said, no, the Transvaal has been thrusted over in the area. And what it then also does is, in some parts of the Kalahari manganese field, it's so nice you can mine it twice. Because it duplicates the Hotazel in some areas. So for some prospecting and mining rights, you can literally mine the Hotazel twice, as long as you're willing to sink a shaft. And then also on the western margin of the Kaapval Craton, here's a very interesting iron ore deposit called Boven-Sequoibaard. And that is Kuruman iron formation that is heavily deformed and faulted. The bedding is overturned, but you get a high-grade iron ore deposit there. Kumba did drill it a couple of years ago, but when I tried to log the core, they drilled it straight down vertically through a deposit where the rocks are tilting 80 to 90 degrees. So logging was out of the question. But that deposit is sitting there and it has not been mined yet. I don't know how economic it is, but and again, it's a wonderful area to walk around and do field mapping, because in South Africa, usually if an ore sticks out, it gets mined almost immediately. So you can actually look at some nice ore sitting in outcrop. And then likely also further upgrade to a lot of these pre-Gamagara unconformity related deposit. Here's a little map. We did hematite age dating across this Griqualand West area. And you'll see the hematite ages, they go as old as 2 to 2.1, probably related to the pre-Gamagara, but you also get this population of hematite sitting at 1.1 to 1 billion years old. So there is a likely that pre-Gamagara unconformity could also have been a horizon along which hydrothermal fluids were also pushed into the system. So concluding remarks, I see the chairperson is staring me down. I'm trying not to make eye contact. That usually wins you an extra 30 seconds. Sorry. So you have to understand the basic geology of the area. So mapping and understanding the surface and subsurface geology is always important, because sometimes the plain sedimentary rock can be your ore as it is, like for example, the Ottazal Formation, but it's also important in identifying the correct protolith. And to the further west of the Craton, structural geology becomes very important, especially with regards to these base metal deposits. I don't talk about it too much because I'm not a structural geologist, but anyway. Then the pre-Gamagara unconformity is such an important feature in the Griqualand West area, because as I say, wherever it cuts through carbonate, you get manganese enrichment. Wherever it cuts through BIF, you get high-grade iron ore. And it could also be a hydrothermal exploration vector for further secondary enrichment that happened. And then also the structures related to the Kaisner-Makwa orogeny can also have potential. Firstly, that is where you host these off-Craton base metal deposits, but also it could be that it had a further big effect, structural and hydrothermal effect for the Transvaal supergroup in the main Griqualand West region. Thank you. That's my talk.